Good morning. Good morning. Audio, video, everything is okay? Just confirm once, please. Good morning. Audio, video, is it okay? Confirm, please. Hello, hello. Wake up. Okay, chalo. So, in this Go Fire program, we are trying to cover. I'm fine, I'm absolutely fine. Okay, so in this Go Fire program, we are trying to cover roughly 70% portion of the syllabus. It is not possible to cover 100% in 3 lectures, you are knowing. If it is possible, then what we are doing in whole year. Here we are trying to cover the important concepts or those concepts where probability of asking question is more. Like in chemistry, we divided this into 3 parts. Physical chemistry, that was covered by Pansar. Inorganic chemistry, that was covered by Birmani sir. And now I'm going to cover the organic chemistry part. Here idea is, hello, voice is coming or not? Hello? One minute, please. In YouTube, voice is coming or not? Please answer. YouTube. Okay. Now you can hear? Okay, chalo, theek hai, good. So, okay, so I was saying that here idea is to cover the important portion of the chemistry here, okay? Like in physical chemistry, we are assuming that roughly 15 question will come from each part. Like we are assuming 15 questions come from the physical chemistry part, roughly 15 questions from the inorganic chemistry part, and 15 questions from the organic chemistry part. And if you are attending this lecture properly, and then after that you are solving the related questions, we can assure that each part will cover on an average 8 to 9 questions, means 8 to 9 questions from the physical, 8 to 9 questions from the inorganic, and 8 to 9 questions from organic chemistry part. It may be more also, but this is the bare minimum what we can assure. That's why if those who are sleeping, please wake up, listen it properly, and after completion of the lecture or class, same day, today only, revise all the questions what are discussed here. You can open your NCERT also meanwhile, so you can go there also. You can, if you are feeling some important points are coming there, you can write in your NCERT, and later on you have to revise everything from there. If you are doing in this way, as I said, on an average out of 45, I can say that 27 to 30 questions will be covered. It may be more also if it is your day or if it is your luck, but 30 questions I can assure. And I think this is more than enough if things are covered in 3 lectures only. 9 hours. Okay. So let's start the discussion. Every point to deal here are important, you are knowing. Okay, so are you ready? Are you ready? Yes or no? Yes or no? Okay. So if you are ready, out of 15 questions of organic chemistry, today's discussion will cover minimum 8 to 9 questions in 3 hours. Okay. First question is, how many sigma and pi bonds are present in each of the following molecule? number of sigma and pi bonds they are asking. So like here two questions are given. I will solve one question and I will give one question as homework that you have to solve after the completion of class. So first molecule is written here. So whenever you are solving this kind of problem, it is better to open the structure. Open means don't operate, just represent bonds, okay? Or I can write the complete structure formula. So for first compound I can write HC triple bond C. You can observe here it is written CC. So next is C double bond C, and next I will write carbon like this, and then again one hydrogen attached here. Double bond is represented here. Then you can observe it is a C and then CH3. This is the structure here. You can easily count number of sigma, like this is sigma bond, sigma here, a triple bond is there, means 1 sigma and 2 pi. Here it is sigma bond, double bond means 1 sigma and 1 pi, single bond means sigma, 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 sigma. So now you can easily count here 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma present. Out of 9 sigma, you can observe this is a sigma bond between CNH, carbon and hydrogen. This is sigma bond between carbon and carbon. It is sigma bond between carbon and hydrogen. This is sigma bond between carbon and carbon. This is sigma bond between carbon and carbon. And these three are sigma bond between carbon and hydrogen. So instead of asking number of sigma bond or total number of sigma bonds, they can ask this also, how many sigma bonds present between carbon and hydrogen. How many sigma bonds are present between carbon and carbon? For example, you can observe here, this is sigma bond between carbon hydrogen, and these three are sigma bond between carbon and hydrogen. Okay, and this is also sigma bond between carbon and hydrogen. Okay, and one more present here. This is also sigma bond between carbon and hydrogen. Okay, got the concept or not? So in this way also, so this is also one sigma bond. Okay, so in this way you can calculate the number of sigma bond. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got the concept or not? So you can observe here they're writing CC bond, sigma bond 4 and CH sigma bond 6. Total is going to be 10. Pi bond is very easy, you can check here. 1 pi bond is present here, second and third. Total 3 pi bonds are present. 1 is present between carbon-carbon double bond in the part of carbon-carbon double bond, and 2 are present in the part of carbon-carbon triple bond. I think you got the concept. Likewise, you can solve next question, that is homework for you. Next question. What type of hybridization of each carbon in the following compound? Hybridization you have to find for the carbon atom here, and idea is same. Here you can observe 1, 2, 3, 4, 5 problems are given. Out of 5, I will discuss 1 or 2. Remaining you have to solve after the completion of discussion. Then only it is going to be fruitful. First molecule I will discuss here, CH3Cl given here. So CH3Cl I can write like this, carbon, hydrogen is going to form single bond there. So I can write like this. How many sigma bonds are present here? 1, 2, 3 and 4. 4 sigma bonds mean this is going to be sp3. You are knowing that hybridization depends on sigma and lone pair count. Sigma and lone pair count. So if, any problem? Okay, no. Few students were saying about the audio. No, it is okay. So if sigma plus lone pair count is 1, hybridization is going to be sp. 2, hybridization is going to be sp2. If it is 3, hybridization is going to be sp3. Likewise, you can think about the higher cases also. Okay, I think you got the idea. So let's discuss the second example here. It is given CH3 twice CO. CH3 twice CO means I can write like this, CH3 twice, CH3 twice CO. I can write like this. This carbon, for this carbon, I will represent hydrogens also. So hydrogen is going to form single bond there. So around this carbon, how many sigma bonds are present? 1, 2, 3 and 4 sigma. No lone pair means this carbon is sp3 hybridized. If I go to this carbon is also going to be sp3 hybridized in same way. And if I go for this carbon, you can observe for this carbon here it is a double bond. Double bond means one is sigma, one is pi. And here 2 bonds are sigma, means how many sigma bonds present here? 1, 2 and 3. 3 sigma bonds, no lone pair, means this carbon is going to be sp2 hybridized. Got the concept or not? So in this way, you can solve other questions also. Simple concept I said, hybridization depends on sigma lone pair count. If sigma lone pair count is 1, if sigma lone pair count is 2, if sigma, I said something. If sigma lone pair count is 2, it is going to be SP. Sigma plus lone pair count is 3, it is going to be SP2. Sigma plus lone pair count is 4, it is going to be SP3. Okay, you can note it down also. Sigma lone pair count 2, SP hybridization. Sigma lone pair count 3, SP2 hybridization. Sigma lone pair count 4, SP3 hybridization. You can note it down also. Beside this, you can write down in your NCERT only. Okay, got it? Chalo, next question. It is written here, expand each of the following condensed formula into the complete structural formula. So to solve this problem, we have to understand what is the difference between complete, condensed and like this. So observe properly. If you are representing bonds in the formula, like here I am representing bonds in the formula, it is known as complete formula. Like you can observe here, each and every bond is represented here. In this case also, it is complete formula. Okay, if same thing like it is written, okay, or I will write one example here. Let's say this molecule given like this. If I write each and every bond, it is complete formula. Now, instead of writing these three bonds, if I write like this, CH3, this is CH2, CH2, CH3, it is named as condensed formula. And how many carbons are there? 1, 2, 3, 4. So if I write by line 1, 2, 3, 4 like this, it is known as bond line formula. Okay, so you can observe here, this is bond line formula. This is a complete formula. And if I'm writing this way, I can name it as condensed formula. Okay, so previous question was here, structure condensed formula is given, and now we have to write the complete structural formula. What is given here? CH3. So CH3 means I can write here CHHH, CH3. Then CH2, so single bond CH2. Then next is given CO. So it is single bond C double bond O. Then next is given here CH2. So CHH. And then next given CH3. So H, H and H. Okay, this is the complete formula there. Okay, means I am writing the bonds, all the bonds I am representing in the molecule, that is known as complete. Okay, next one. Next question. Now, this is given, and you have to write the IUPAC name. So while writing the IUPAC name, first is a selection of parent carbon chain. Here you can observe, this is going to be the parent carbon chain. It is going to be parent carbon chain. Okay or not? Now in this selected chain, we have to go for the numbering. What is the sequence for nomenclature? Firstly, select the parent carbon chain, then go for the numbering of parent carbon chain. So here, if I go from left to right, see this CH3, this CH3 and this CH3, all are substituent. Okay, if I go from left to right, it will be coming number 1, it is going to get number 2. 1, 2, 3, 4, 5, 6, 7, 8. So left to right, what numbers are coming there? 2, 5 and 6. If I go from right to left, I will get number like this: 1, 2, 3, 4, 5, 6, 7 and 8. So here we will get number 3, 4 and 7. So left to right number coming 2, 5, 6, and this side number coming 3, 4 and 7. So this is giving me lower number. Start from 2 and this start from 3 actually. Okay, so lowest locant rule is suggesting we have to go like this. Okay, and this number is going to be wrong. Now then you can observe here key. So this is wrong, so I'm ignoring it. So number 2 position is methyl, number 5 position is methyl, number 6 position also methyl. So I can name it as 2, 5, 6 trimethyl, and total carbon count 8, and all are single bonds, so I can name it as octane. Okay, so you can observe there it is written here 2, 5, 6 trimethyl octane. With the same logic, you can solve next problem also. Idea you're knowing. A few questions I will solve and remaining you have to solve. Now, for the IUPAC nomenclature, this priority order is very important. For the IUPAC nomenclature, priority order of the functional groups is very important. If you're not knowing, memorize it properly. Highest priority given to the carboxylic acid group, then sulfonic acid, then it is ester, acid halide, it is amide, nitrile or cyanide, aldehyde, ketone, alcohol and amine. After that it is given alkene or alkyne. Okay, alkene, alkyne, they are not writing any priority sequence because in this case there is no difference until unless condition is not symmetrical. Okay, so considering this one, we have to solve few problems here. For example, check it please. This is given, this compound is given. Now in this compound, rule is very simple. You have to select the parent carbon chain first. Okay, if I select the parent carbon chain, you can check it here. This is the parent carbon chain. This is the parent carbon chain. Now in this selected chain, you can observe this OH is a principal functional group and this CH3 is a substituent. Rule is, when you are selecting the parent carbon chain and you are having there some principal functional group, so first priority is give lower number to the principal functional group, then give lower number to the multiple bond, then give lower number to the substituent. So if I start from this side, PFG will get higher number. If I start from this side, principal functional group will get lower number. So obviously I will go from this side because this numbering is giving me lower possible number for the principal functional group. This is the substituent and it is methyl, so I can name it as a 6-methyl. 6-methyl, it is a total carbon 8, so I can say oct. All are single bonds, so ane, so I can name it as a 6-methyl octane. And in 3 position it is having OH, means ol, so 3-ol. So, and one more point, when I'm writing here this thing 6-methyl octane, 6-methyl octane 3-ol. So here when I'm writing this thing ane, octane, this is going to be deleted because rule is very simple. After ane, ene or ine, if a, e, I, o, u or y present, then this is going to be deleted. This is the important part because sometimes they are playing trick by giving this kind of situation. You can observe in the name here, it is written AN only, AN written here, ANE is not written, this is deleted here. Because just after this AN, what is present here? O is present here. Logic is clear to you or not? Chalo. Next question, you can observe here, this is the parent carbon chain. Number 2 and number 4 both are ketone. Both are ketone here. And there is no higher priority group, means they are principal functional group. Principal functional group. Both can act as PFG here. I will name them as own. And you can observe, I will start from numbering from this side because this will give me lower number to the PFG. So I can name it as a hexane 2,4-dione. When I am saying here 2,4-hexane 2,4-dione. So you can observe here it is ane, and after this it is not A, I, O, U, Y, it is a D actually. So this E will be retained here. You can check in the name also. Here it is written hexane 2,4. Here this E is retained. Here this E is retained. Logic is clear or not? Likewise, you can solve next problem also. What happened? This is given. Now in this given compound, this is the parent carbon chain, this is the parent carbon chain. Okay or not? Now in the priority table, what I said to you or which is known to you, you can check carboxylic acid is having highest priority here. So this is going to become PFG. If higher priority group become PFG, then lower priority group becomes substituent. So for this ketone, this double bonded oxygen is going to act as a substituent, and if it is acting as substituent, I can name it as oxo. Okay or not? So now I can observe here number 5 position is having substituent oxo. So I will name it as a 5-oxo. 5-oxo. Total carbon count 6. So I can name it as a 5-oxo hexane 1-oic acid. 1-oic acid, and this is going to related logic is known to you. Or if for this part I can directly write this also, hexanoic acid. For this part I can simply write hexanoic acid. Okay, logic is clear. Next one. Okay, so this is the explanation for same question. Go for the double bond cases. For double bonds, rule is very simple. In case of double bond or carbon-carbon double bond or carbon-carbon or carbon-carbon triple bond, in case of carbon-carbon double bond or carbon-carbon triple bond, you have to give continuous numbers. For example, 1, 2 allowed, 2, 3 allowed, 3, 4 allowed, or I can write like this also, 3, 4 allowed. Continuous number 1, 2, 2, 3, 3, 4, 3, 4 like that. They are possible. But if you are giving discontinuous number, for example, let's say carbon-carbon double bond or triple bond given, and I'm giving number 1, 3 not allowed, 2, 5 not allowed, 1, 4 not allowed, 1, 6 not allowed. Discontinuous numbers are not allowed for the carbon-carbon double bond or triple bond. This rule is not valid. This rule, what I said here, is not valid for the benzene. This rule is not valid for benzene. Logic is clear? Logic is clear to you? Please answer. In case of carbon-carbon, in case of carbon-carbon multiple bond, what to give? Continuous number. What to give? Continuous number. And this rule is not valid for, this rule is not valid for benzene. Understood the concept? Understood the concept or not? Please reply quickly. Yes or no? Wake up. Yes or no? Yes, very good. Chalo, good. YouTube guys also, please wake up. Don't sleep. Chalo. So now this question is given. This question is given. Here you can check when I'm numbering. I'm not having any principal functional group or any substituent. Okay, simply this multiple bond is given here. So I will give continuous number to the multiple bond. You can check numbering given like this 1, 2, 3, 4, 5, 6. Logic is clear or not? Like logic is clear or not? So here I can name it as cyclohexene. Here any other group not present, so I can simply write cyclohexene. Come to the next case. Come to the next case. Very important example. Very important example. This is given to us. Now in this case, someone may think to number, okay, I will write two possibilities, then better clarity will come. Someone may think to write like this 1, 2, 3. And other person can think to write like this 1, 2, 3. Sir, I am thinking to write like this also, sir. Sir, I am thinking to write like this 1, 2, 3, 4, 5 and 6. Okay, chalo, no problem, let's discuss. What is the rule there? When you are numbering, try to give lower number to the PFG. So in this example, no one is PFG. Few groups like nitro, halo, ether, they are always acting as a substituent. Few groups like nitro, halo, ether, they are always acting as a substituent. So this NO2 is a substituent. This NO2 is a substituent. So what is the rule? Try to give lower number to the PFG. Lower number to the PFG. Then second priority, lower number to the multiple bond. Multiple bond means carbon-carbon double bond or carbon-carbon triple bond. And then lower number to the substituent. Lower number to the substituent. Getting or not? So here, if I give number 1 to this nitro, means I am giving lower number to the substituent. Substituent getting number 1 and multiple bond getting number 2 here. And logic is firstly give lower number to the PFG. In this given example, no one is PFG. Then lower number to the multiple bond. So if I am selecting and then substituent. Substituent is coming at the priority number 3. So if I am going for this numbering, what I am doing actually, I am giving lower number to the substituent, not to the multiple bond. So this selection not correct. If I go for the next case, here I am giving one number to the multiple bond. I am not saying lower number means always 1. Here it is possible to give 1, that's why I am giving. Okay, so here lower number is given to the multiple bond, and then sir, why you're not going like this 1, 2, 3, 4, 5, 6? If you're going like that, multiple bond will get number 1 and 6. Is it allowed? Answer is not allowed. So here, this selection is correct because here I'm giving lower number to the multiple bond. Logic is clear or not? And then going this direction, so lower possible number can be given to the substituent also. Okay, then I can name it very easily. Number 3 position is nitro group, so I can say I can name it as a 3-nitro cyclohexene, or simply I can write cyclohexene also. Chalo, very good. Understood the concept. Now you can go for next example. You can go for next example. Here, if I compare, I will write here so visibility will be better. If I compare this example with this one, I will compare these two examples side by side, so you will understand the concept here. In case of this is OH. OH is a principal functional group here. And here, this NO2 is a substituent. This NO2 is a substituent. So in first case, my PFG is given. PFG is given. So my priority is give lower number to the PFG. So I will give one number to this. I'll go like this 1, 2, 3. In this case, NO2 is not PFG. The next priority is what? Give lower number to the multiple bonds. I'll write like this 1, 2, and 3. Logic is clear. So here I will write this as a cyclohexene 1-ol. And obviously E will be deleted. Logic is discussed. Understood the concept or not? Please answer. Logic is clear to you? Understood? Yes or no? Yes or no? Arey reply yaar. Answer quickly. Time is less and concepts are more. If you're not very prompt, it will waste time, okay? Yes, 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 yes. Yes, yes, yes. Very good. Chalo. Any doubt? Any problem? Chalo. Let's go for the next question. Now here you can check the benzene cases taken here. So when benzene cases are given, first thing, to avoid any kind of confusion there, if they're writing double, single, double like that, ignore this one and draw something like this. So now, if you're drawing something like for the benzene cases, confusion will not happen related to the multiple bond. Logic is clear? Understood or not? Benzene cases given, then immediately draw like this for the IUPAC nomenclature, so there will be no confusion related to the multiple bond. Now in this given compound NO2ClCH3, all are substituent. I said one point, halo group like chloro, bromo, iodo, fluoro, they are always a substituent. Nitro always a substituent. Ether always a substituent. So here all are substituent, and multiple bond of benzene is meaningless for the IUPAC nomenclature. Here I can give discontinuous numbers also. Okay or not? So all are substituent. So think in what sequence I can give lower number to them. Here no PFG, multiple bond of benzene is useless for the IUPAC nomenclature. Then what left? Substituent there. In this example, substituent only. So if I'm giving like this 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Now if I'm giving like this 1, 2, 3, 4, what numbers are coming there? 1, 3 and 4 coming. If I'm giving like this 1, 2, 3 and 4, what numbers are coming? 1, 2 and 4. 1 to 4. Obviously 1 to 4 is lowest locant rule. Following here lower number given, so I'll go for this numbering. Okay, now this is methyl M chloro C and nitro N. So alphabet A B C D to you are knowing or not? A B C D E F G, knowing or not? That's obviously knowing here. If not knowing, please take admission in K1. Okay, so I can name it as 2 chloro 1 methyl 4 nitro benzene. Okay or not? Okay, chalo. Next example. Here I'll discuss this example. Here you can check NH2 is a principal functional group. NH2 is a principal functional group. Here lowest number given to this one. These two are substituents. It is methyl and this one is ethyl. Okay or not? So I can name it as a 4 ethyl 2 methyl, and it is a, if I have this part only, assume only this thing is present. If these two are not present, this is aniline molecule. So now in aniline at number 4 position ethyl is attached and number 2 position methyl is attached. So I can name it as a 4 ethyl 2 methyl aniline. Chalo, logic is clear to you. Same concept for this also. Here OH is principal functional group. So I'm trying to give lower number to the PFG, and here I'm not caring about the number of the multiple bond. Chalo, next question. Few molecules are given there and you have to represent the kind of bond breaking there. Okay, in terms of the heterolytic cleavage, two type of bond fission are there, homolytic and heterolytic. For example, let's say AB bond is there, breaking like this or breaking like this. It is heterolytic bond fission. In first case, it will break like A plus and B minus. You can observe electron density is going towards B. So B will become minus and A become plus. If I'm breaking in this manner, A become minus and B become plus. This is the example of heterolytic bond cleavage. If I am breaking bond in this way, it become A radical and B radical. This is known as homolytic bond fission. Okay, so now question is here, using curved arrow notation, show the formation of reactive intermediate when following covalent bond undergo heterolytic cleavage. Okay, first example given there, CH3. First example is given here, CH3, SCH3. CH3, SCH3. Okay, so here you are knowing out of carbon sulfur is more En, so bond I will break towards the sulfur. So this part becomes CH3 plus and this part become SCH3 and sulfur is getting minus charge here. Okay or not? Next example given, CH3CN. So here in this case this is sp carbon and this is sp3 carbon, and En of sp carbon is more than sp3. En order you're knowing sp3, sp2 and sp. Okay, so here sp carbon is more En, I will break like this. So this part becomes CH3 plus and this part becomes Cn minus. Next example is given, CH3Cu, very important case. CH3Cu, you knowing copper is a metal. If metal given, metals have tendency to acquire positive charge. So if I break like this, let's say I'm breaking like this, I will get copper minus, not allowed there, not allowed, means this bond breaking is not correct. So how to break here? CH3Cu, copper is metal and metals have tendency to acquire positive charge, so I will break in this way. So this becomes CH3 minus and this become copper plus. Okay or not? So if metal is attached, for example, any case I can generalize. Let's say this condition given, carbon and metal. So metal will acquire positive charge. And how metal can acquire positive charge? If I am keeping electron away from metal in this way. So this part become minus and this part become plus. Chalo, it is good question and probability is also there from this part to come question in the exam. Next is given, giving justification categories following molecule ions as a nucleophile or electrophile. Nucleophile or electrophile. Okay, so it is very easy question here. Okay, check it quickly. First is written HS minus, minus charge present means it is a nucleophile. BF3, it is electron deficient means it is electrophile. Nucleophile means Nu. Okay, so I will write here Nu one side, E other side. Nu means nucleophile, E means electrophile. SH minus, again minus charge present, it is going to be nucleophile. So HS minus nucleophile. BF3 electron deficient, it is going to be electrophile. Next is given there CH3 thrice N. CH3 thrice N. Here nitrogen is containing lone pair and octet is also complete. Lone pair and complete octet. This can be lone pair donor, means nucleophile. So this one I will write in nucleophile part CH3 thrice N. Cl plus charge electrophile. Sometime nucleophile represented like this also. I will tell you one simple representation, you will get idea. Nucleophile I can represent like this, Nu lone pair, or I can represent Nu minus. So those cases where lone pair is present and octet is also complete, they can act as nucleophile, or minus cases also can act as nucleophile. Positive charge E plus cases or electron deficient cases can act as electrophile. One important example is there, if dichlorocarbon is given. Here I can have lone pair, but it is electrophile because it is electron deficient. If something is electron deficient, that is going to act as electrophile. So you can check. Next is positive charge, electrophile. It is a minus charge and lone pair also. Octet also completed is going to be nucleophile. Plus charge, it is electrophile. Understood the concept? Chalo. Next problem, next concept, inductive effect. Inductive effect means what? It is very easy to understand. If, let's say, this condition is given. So CCl in this bond, carbon-chlorine bond, chlorine is more electronegative. This will attract electron here. So chlorine become minus and carbon become plus. Now this carbon will attract electron from the previous one, this carbon. So it become double delta plus. Here double delta plus is smaller than first, means delta plus. So when this bond is becoming polar due to the adjacent polar bond, it is known as inductive effect. Inductive effect is distance dependent. As you are going away from the group, inductive effect is going to decrease drastically. Okay, so here I can simply answer delta plus is more than double delta plus. Okay, got the concept or not? So in this case you can clearly observe here chlorine minus, next is delta plus, and next is double delta plus. Here double delta plus is less than delta plus. Okay, this is what inductive effect. Next is, write the resonance structure of CH3CO minus. What is given here? CH3 C double bond O minus. You can observe here it is minus a single double. Minus single double, it can go for the resonance effect. Okay, minus single double. Whenever you have pi bond and adjacent position, pi bond is there and alternate position of pi bond is having plus charge, minus charge, lone pair or radical, this can go for the resonance. Or if you have alternate pi bonds, this can also go for the resonance provided orbitals or p orbitals are parallel. Okay, so if you have alternate pi bonds or alternate pi bonds, in this case also resonance possible, or if you have plus minus lone pair and radical at the alternate position of pi bond, then also resonance is possible provided p orbitals are parallel. Understood? Got the concept? So here in this example you can check it easily. Pi bond single minus, this condition is followed, it can go for the resonance. How to draw resonance here? Very easy concept. Minus, away from minus and towards plus. Away from minus or towards plus. It is a minus. I'll go away from minus, I'll delocalize in this manner. I'll go away from minus, I'll delocalize in this manner. So, and resonance structures are represented by this double-headed arrow. And next structure I will get here CH3C, O minus double bond O. Got the concept now? So here, these two are the resonance structures of this carboxylate ion, and you can observe both the structures are identical. If resonance structures are identical like this or like this, then bond lengths which are going for resonance are equal. So here I can say both carbon oxygen bond lengths are equal. Let's say this bond is given X and this bond is given Y. I can answer here bond length X is equal to Y because they are identical resonance structures. Okay or not? This is the concept here. This is the concept here. Understood logic? Okay. Now next one. Here, resonance structure of benzene is also explained. In case of benzene, you are knowing, in case of benzene, if I am writing this structure, this is known as Kekulé structure. And always remember, resonance structures are not real structures, they are hypothetical. Resonance structures are not real, they are hypothetical. What is real structure? Resonance hybrid. What is real structure? Hybrid. So hybrid is real and RS, resonance structure, is hypothetical. So in case of benzene, in case of benzene, in case of benzene, in case of benzene, if I am writing this double, single, double, it is resonance structure of benzene and RS are not real. Here double, single, double, double, single, double. I can delocalize in this way. I can delocalize in this way and I will get next structure. So this double bond formed here, pi bond formed here like this. These two are the RS of benzene, and you can observe both are identical. So based on these two, I can write the real structure that is known as resonance hybrid. Resonance hybrid, I can draw something like this. This is the real structure of benzene. And one more point, I said earlier, I am repeating same thing again. In case of benzene, you can observe both RS are identical. So here I can say all carbon-carbon bond length, because you can check here, resonance taking place in the carbon-carbon part. All carbon-carbon bond length, CC bond lengths of benzene, CC bond lengths of benzene are equal. Why equal? Because of the equivalent resonance structures. Okay. Benzene has CH bond also. Benzene has CH bond also. So in case of benzene, we have 6 CH bonds. We have 6 CH bonds. So let's say statement given by the examiner. In case of benzene, all bond lengths are equal. False. All bond lengths are equal for benzene. It is not correct. Why not correct? Because we have CH bond. This is CH bond. And this is a CC bond. So obviously CH bond is less than the CC bond here. Okay. So I cannot say this thing, all bond lengths in benzene are equal. What I can say, all CC bond lengths in benzene are equal. CH bond is different than CC bond. Okay. CC bond lengths are equal in benzene. Okay. Chalo. Next question. Okay. Check it here. 3 intermediates are given. The carbocations are given here. 1, 2, 3. Sorry, 4 are given. Now, in first case, you can observe this plus charge is having plus charge directly attached carbon, alpha carbon, and hydrogen attached to alpha carbon is alpha H. So here 3 alpha H, 3 alpha H, 3 alpha H. First carbocation is having 9 alpha H. First carbocation is having 9 alpha H. For next one, it is given CH3 twice CH plus. So I can write like this, CH3, CH3 plus. Carbocation, next carbon alpha, this carbon also alpha. 3 alpha H here and 3 alpha H here. This having 6 alpha H. In this case, 3 alpha H present and here alpha H count is 0. If alpha hydrogens are more, hyperconjugation effect is more. Hyperconjugation effect is observed in the case of carbocation, carbon free radical, and carbon-carbon pi bond like alkene. If alpha hydrogen present, is it clear or not? So here alpha hydrogen, 9 alpha H, 6 alpha H, 3 alpha H, and no alpha H here. So obviously more alpha H, more hyperconjugation effect, more stability of carbocation, more stability of carbon free radical, and more stability of alkene also. Okay, got the concept or not? Here they are writing also hyperconjugation is also possible in alkenes and alkyl arenes. Got the concept or not? So this is also very important point here. So if I observe stability of carbocation, first is more 3 degree, more alpha H more stable than next one, 6 alpha H. 6 alpha H more stable than 3 alpha H, and 3 alpha H more than 0 alpha H. If it is carbon free radical, in radical also hyperconjugation possible, so same trend will come. If radical given, then also first is most stable and last one is least stable. If carb anion given, trend will be opposite of the carbocation in this case. So if minus given there, assume it is minus carbanion, then this is the stability order. Okay, chalo, move to the next question. They're asking here why CH3 thrice C plus is more stable than CH3, CH2 plus and CH3 plus. You draw the structure, you will get answer. First is given CH3 thrice C plus, CH3 thrice C plus. Next is given CH3 twice CH2, CH3 CH3CH2, and next is given CH3 plus. Next is given CH3 plus. In first case, you can clearly observe this is the carbocation. Next carbon is alpha. This is alpha carbon, alpha carbon, alpha carbon. This alpha carbon has how many alpha H? 3. Here also 3. Here also 3. This has 9 alpha H. Same problem actually. Here 3 alpha H and here no alpha H. So now answer, who is more stable? Which one is more stable? Please answer quickly. Let's say this is 1, this is a 2 and this is a 3. Which one is more stable? Please answer. Which one is more stable? Answer quickly. Which one is more stable? Are answer yaar. Don't sleep, answer please. Which one is more stable? Yes, very good. Chalo. Chalo, very good, very good. First is more stable. Chalo. Okay. Out of 1, 2, 3, in which case hyperconjugation not possible. Out of 1, 2, 3, in which case hyperconjugation not possible. Out of 1, 2, 3, in which case hyperconjugation not possible. Very good, very good. All are giving correct answer. 1140. Are you sleeping? This is number 3. This is number 3. Here hyperconjugation not possible. Logic is clear. Logic is clear. Chalo. Here carbocation is given, and you know in carbocation here is having sigma 3 sigma bond. In this example it is going to be sp2 trigonal planar. So next is the structure of methyl carbocation. Next is the structure of methyl carbocation. In case of methyl carbocation, you can observe this carbon is having 3 sigma bonds, so it is going to be sp2. In the beginning only I said sigma plus lone pair count will decide hybridization. If sigma lone pair count 2, sp. If sigma lone pair count 3, sp2, and if sigma lone pair count 4, then sp3. Okay or not? So here sigma 3 sigma no lone pairs sp2 planar structure, and since hybridization is sp2 means one p orbital is pure and that is perpendicular to the plane of CH3. Okay, so this structure of carbocation which is a sp2 hybridized trigonal planar, and this vacant 2p is perpendicular to the plane of CH3 plus carbocation. Okay, chalo. Next one. Methods of purification of organic compounds. Methods of purification of organic compound. These are the methods for purification: sublimation, crystallization, distillation, differential extraction, and chromatography. Here principles are very important. In what condition we have to go for particular method. Okay, for example, sublimation. If organic compound is sublime, and impurity is non-sublime, then I can go for this technique. Okay or not? Crystallization. Organic compound is having high solubility, high solubility at high temperature and low solubility at room temperature, then I can go for crystallization. Distillation, if crystal liquids have sufficient difference in boiling point, large difference in boiling points. If it is condition for the simple distillation, it is the simple distillation. If small difference is present, small difference in boiling point is present, if a small difference in boiling point is present, then we can go for the fractional distillation. Many distillation techniques are there. Okay, I'm writing here two important cases. If there is two miscible things, or maybe more than two also, they having large difference in boiling points, go for simple distillation, and if they have a small difference in boiling points, go for the fractional distillation. For simple distillation, we have one very important example. If it is a chloroform aniline mixture that is separated by, or that is purified by the simple distillation, chloroform aniline mixture, PHNH2, okay. Fractional distillation, one very important example, different fractions of crude oil are separated by this technique. Okay, if they are asking steam distillation, two important examples. One, aniline water mixture, and second example is ortho and para nitrophenols. Differential extraction, if organic compound is more soluble in the organic solvent. Differential extraction, if organic compound is more soluble in organic solvent than water. And chromatography is two types of chromatography are there: adsorption chromatography and partition chromatography. In adsorption chromatography, we have two examples: thin layer chromatography and column chromatography. Partition chromatography, one example, paper chromatography. Sometimes they are asking direct question. Paper chromatography is the example of, answer is partition chromatography. Very easy to memorize by paper, P for paper, P for partition. P for paper, P for partition. Paper chromatography is the example of partition chromatography. So other two, thin layer chromatography and column chromatography, they are the example of adsorption chromatography. Here they can ask one very good question here, how to find the purity of organic compound. So purity of organic compound can be determined by the melting point, by the boiling point. Purity of organic compound can be determined by melting point or boiling point. And nowadays we have better techniques. They are chromatographic and spectroscopic technique. So we can find the purity of organic compound by melting point, by boiling point, by chromatography, and by spectroscopic techniques. Okay, melting point and boiling point are the old techniques, and chromatography and spectroscopic techniques are the latest technique. Obviously they are advanced and they are better. So here they can ask one very good question, how to find the purity of given organic compound. One line answer, it can be predicted or it can be determined by the melting point or by boiling point or chromatographic techniques or spectroscopic technique. Okay or not? If they are asking how to find the melting point, how to find the purity of organic compound by the advanced techniques or better techniques, more efficient techniques, then we have to take chromatographic technique or spectroscopic techniques. Chalo, next part, detection of the organic compound. Here one very important question they can ask, which elements are detected by the Lassen test? Answer is nitrogen, sulfur, halogen and phosphorus. Which elements are detected by the Lassen test? Answer is nitrogen, sulfur, halogen and phosphorus present in the organic compound. You can read line there, nitrogen, sulfur, halogen, phosphorus present in an organic compound are detected by the Lassen test. Okay or not? Here, if nitrogen is present in the organic compound, and if it is organic compound carbon already present, it will make sodium cyanide when I'm making fusion extract there, named as sodium fusion extract. Sulfur, Na2S, and halogen, NaX. Okay, so what is the important concept here? Lassen test can be used for the qualitative analysis or used to detect nitrogen, sulfur, halogen, phosphorus present in the organic compound. If nitrogen is present in the organic compound and you are making sodium fusion extract, this line is very important, sodium fusion extract. Obviously, if it is sodium fusion extract, we have to use sodium to fuse the organic compound. That's why sodium is taken here. It will give cyanide, NaCN. It will give NaCN, and this NaCN, when treated with the FeSO4 in the presence of H2SO4, it is giving Prussian blue. Is it clear or not? It is giving Prussian blue. Directly memorize this color. Sodium cyanide is treated with the ferrous sulfate in the presence of H2SO4. It is giving Prussian blue. In case of Na2S, if it is treated with the lead acetate PbCH3CO twice, it will give black precipitate of PbS. Okay, and in case of NaX, it can be NaCl. In case of NaX, it can be NaCl, it can be NaBr, or it can be NaI. NaCl, NaBr, NaI, when they are treated with the AgNO3 silver nitrate, treated with the silver nitrate, first is giving precipitate, white precipitate of AgCl, this is giving pale yellow precipitate of AgBr, and this is giving yellow precipitate of AgI. Okay, white precipitate, pale yellow precipitate, and this is giving intense or dark yellow precipitate. And if I dissolve them in ammonium hydroxide, this is easily dissolving, this precipitate, ammonium hydroxide solution, obviously. This is having this is also getting dissolved, obviously less than first, and this is not getting dissolved in the ammonium hydroxide. This is the test of halogen. Logic is clear or not? Okay, here when we are adding silver nitrate, along with this we have to add some nitric acid also. So they can ask before adding silver nitrate what to add in this test of halide. Answer is nitric acid. If some disturbing ion or interfering ions are there, they will be removed. Geldar's method. It is the quantitative estimation of nitrogen. In this case, the most important point is the compound containing nitrogen is heated with the concentrated sulfuric acid. The organic compound having nitrogen is heated with the concentrated sulfuric acid in the presence of CuSO4, giving ammonium sulfate, which on treatment with the excess of NaOH give ammonia, and this ammonia can go for the titration to find the percentage of nitrogen. Okay or not? So here, organic compound containing nitrogen is heated with the sulfuric acid in the presence of copper sulfate in Geldar's flask. This will give ammonium sulfate, which is treated with the excess of sodium hydroxide to get ammonia, NH3, and this ammonia is titrated to find the percentage of nitrogen in organic compound. And the more important point is, what are the cases where this Geldar's method is not applicable? So very important case, if any organic compound is having azo group, N double bond N group, this is known as azo group. Any organic compound is having nitro group, or any organic compound if it is having nitrogen in the ring, in these three cases the Geldar's method is not applicable. Azo group, nitro group, and N in ring, nitrogen present in ring, it is the part of ring, then Geldar's method is not applicable. Geldar's method is not applicable to the compounds containing nitrogen in nitro, this example, and azo group, this example, and nitrogen present in the ring. Read this line, nitrogen present in the ring. For example, pyridine means nitrogen is the part of ring. Then Geldar's method is not applicable. Next question. In Carrier's method of estimation of halogen, 0.15 gram of an organic compound gave 0.12 gram of AgBr. Find out the percentage of bromine in the compound. This type of questions are very easy. If you know in basic mole concept or fundamentals of the mole concept, you can easily solve all the questions related to the quantitative estimation. For example, here 0.12 gram of AgBr given. So moles of AgBr, I can write 0.12 divided by the molecular mass of or molar mass of the AgBr. So AgBr, Ag is 108 and bromine is 80. This is going to be 188. This is going to be 188. This is the moles of AgBr. 1 AgBr contain 1 bromine. So moles of bromine is equal to 0.12 divided by 188. So I can find percentage of bromine here is equal to mole of bromine is 0.12 divided by 188. So mass of bromine is going to be multiplied by its atomic weight, and that is 80 divided by the weight of organic compound given here 0.15 multiplied by 100. Simple concept is if you want to find the percentage of any element, so percentage of element is equal to weight of that element divided by the total weight of organic compound multiplied by 100. If you want to find percentage of any element, concept is very simple. Weight of that element divided by the weight of organic compound multiplied by 100. Here I want to find the percentage of bromine. So I am writing here weight of bromine divided by the weight of organic compound multiplied by 100. It is given here different chain isomers of C6H14. Very easy question. C6H14, this is general formula of alkane. You are knowing alkane general formula is CnH2n plus 2. So C6H14, it is following the general formula of alkane. Okay, general formula of alkane is followed here. Total carbon count 6, and now they are asking number of structural or chain isomers here in this case. Total carbon count 6. So first possibility, I can draw 6 carbon chain. 1, 2, 3, 4, 5, 6 carbon chain. When you are solving this kind of problems, go in the decreasing order of the chain length. Go in the decreasing order of chain length. First I am writing here 6 carbon chain. Next I will write here 5 carbon chain. So 1 carbon is extra. For that extra carbon, one possibility I can attach to carbon number 2. Don't attach to carbon number 1. It is the previous example. Okay. Or I can attach extra carbon at carbon number 3. 6 carbon chain. Then 5 carbon chain. What next? 4 carbon chain. If I am going to the 4 carbon chain, 1, 2, 3, 4. Total carbon count is 6. It is C6 here. Means 2 carbons are extra. So one possibility I can attach these 2 extra carbon to the different carbons. And I said now, don't attach to this terminal carbon. Otherwise, it is going to be previous category which is already written. So 4 carbon chain, 2 carbons are extra. One possibility I can attach to different carbons, and next possibility I can attach to the same carbon. Got the concept or not? Okay, so 6 carbon chain, 1 possibility, 5 carbon chain, 2 possibilities, and 4 carbon chain here, 2 possibilities. So 1, 2, 3, 4, and 5. Okay. So 5 isomers are coming here for the C6H14. Next is sodium salt of which acid will needed for the preparation of propane. Chemical equation for the reaction. Okay. Decarboxylation reaction. Concept I will tell you, you can easily find answer here. Sodium salt of carboxylic acid is heated with the soda lime. Soda lime is mixture of sodium hydroxide and calcium oxide. Then very easy method is there. This part will come out as Na2CO3. This part will come out as Na2CO3. So what is left here? This R and this H, they will bind and it's going to become RH. Means if I have carboxylic acid or monocarboxylic acid of N carbons, I will get alkane of one less carbon. Sir, why one less carbon? Because this one carbon is gone as Na2CO3 in the decarboxylation reaction. So now here question is about the preparation of propane. Propane means how many carbon? 3 carbons. So if I want to make alkane of 3 carbons, I will take carboxylic acid, monocarboxylic acid of 4 carbons. So now think how I can make propane. If I take this compound CO minus Na plus, heating with the soda lime NaOH CaO, then this part will come out as Na2CO3. And what left here? These 3 carbons left means I will get propane. One more possibility is there which is very important. If I have this condition CO minus Na plus and I am heating with the soda lime NaOH CaO heating, this part will come out as Na2CO3. So what left there? Carbon, 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 and this hydrogen bind with this carbon. So I'm not representing hydrogen, so I'll get this structure. And you can write same thing like this also. It is also propane. So these 2 compounds or these 2 monocarboxylic acid sodium salts can give propane by the decarboxylation reaction. Next is about the geometrical isomer. In case of but2ene, I have 2 geometrical isomers. But2ene is having 2 geometrical isomers. One is a cis, another is a trans. Cis, you can observe CH3. These 2 CH3 are present same side, cis. Here, these 2 CH3 present opposite sides, trans. Now, so cis and trans are there. In case of cis, dipole moment of this CH3 and this CH3, they are added. It is going to be non-zero. And here, dipole moment of this CH3C bond and this CH3C bond, they are opposite. They will be cancelled. Equal and opposite, they will be cancelled. It is going to become 0. Means I can say dipole moment of cis but2ene is more than a trans but2ene. For example, here for cis they are adding 0.33 dBi and for trans it is written 0. So dipole moment of cis but2ene is more than trans but2ene. Why? Because in case of trans but2ene, dipole moment vector of this CH3C bond and this CH3C bond, they are equal and opposite, so they will be cancelled. It becomes 0. Okay, next concept. It is given to you, compound is given hex 1ene and hex 1ene is given. So hex means how many carbons? 1, 2, 3, 4, 5, 6. Hex 1ene, one position has double bond. I am not representing hydrogens. Okay. One condition given HBr with peroxide and one condition given without peroxide. So one condition peroxide given, another condition 1, 2, 3, 4, 5, 6 HBr without peroxide. Concept is very easy. I will write hydrogen here. This is CH3, CH2, 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 CH, and this is CH2. Here also I can write this is CH3, CH2, 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 CH, and this is CH2. Okay. Method is very easy. Method is very easy. Here HBr only given, no peroxide. Means it is H plus and Br minus. H plus and Br minus. Now check this double bond, carbon-carbon double bond. This carbon has 1 hydrogen, this carbon is having 2 hydrogen. So which carbon is having less hydrogen? Answer is this one. So in this case, bind bromine to the double bonded carbon who is having less number of hydrogen. That is known as Markovnikov's rule. So go for the double bonded carbon. This is having 1 hydrogen and this is having 2 hydrogens. So bind Br to this one. So 1, 2, 3, 4, 5, 6. It is a C. I am representing hydrogen for the important case. This was given. I will break this pi bond. I will break this pi bond, and I will bind bromine to this carbon and hydrogen this one. This is known as Markovnikov's rule. Okay or not? If peroxide given, then it is giving Br radical, bromine radical. In this case, you have to bind bromine to the carbon having more hydrogen, double bonded carbon. So this carbon is having 2 hydrogens and this is having 1 hydrogen. I will bind bromine here. So 1, 2, 3, 4, 5, 6 bind here. Okay. This is clear to you? Understood? Okay, so 2 cases are given here, HBr with peroxide and without peroxide. If HBr given without peroxide, then bind bromine to the double bonded carbon who is having less number of hydrogen, Markovnikov rule. In this case, I am ignoring mechanism and rearrangement concept because time is limited, so we have to focus on the important point. And this second case, I will bind bromine to the double bonded carbon having more number of hydrogen because peroxide given here. This is known as peroxide effect also. Okay. So class 11th part is over. Now let's move to the class 12th part. Okay. Here I will discuss one small concept. In case of aromatic compounds like benzene, the main reaction is electrophilic substitution reaction. In case of aromatic compounds like benzene, main reaction is electrophilic substitution reaction. I can name it as electrophilic aromatic substitution represented by symbol Se. Okay. Now here, if electrophile is given, hydrogen atom of the benzene will be removed and electrophile bind there. How I can generate electrophile? That is important. If H2SO4, HNO3 given, or sometimes they can give only nitric acid in few cases, this is going to generate electrophile NO2 plus. If halogen XX, for example, ClCl, AlCl3, Lewis acid given, this Cl bind with the AlCl3. So Cl minus bind with the AlCl3, it becomes Cl plus and AlCl4 minus. This chlorine plus electrophile is generated. If CH3Cl, AlCl3 given, this Cl minus bind with the AlCl3. So Cl minus bind with the AlCl3. This part become AlCl4 minus and giving electrophile CH3 plus. If only concentrated sulfuric acid given, or sometimes they can give fuming sulfuric acid or oleum. In that case, it is generating electrophile SO3. By this, what we are learning? Electrophile can be neutral also. If knowing this concept, you can solve all the electrophilic substitution reactions of aromatic compounds. For example, if benzene is given, and I am giving nitrating mixture HNO3, H2SO4, what product will form? Nitrobenzene. In this case, benzene not having any group, so I can bind NO2 to any carbon. If sulfuric acid concentrated given, then it is going to give a product SO3H, benzene sulfonic acid. If Cl2, AlCl3 given, few minutes back I said Cl2, AlCl3, or they can give FeCl3 also. This Cl minus bind with the AlCl3, generate electrophile Cl plus. Here I will get product chlorobenzene, and if I take excess of chlorine, all 6 hydrogen replaced by chlorine, I'll get hexachlorobenzene. If CH3Cl is given in the presence of AlCl3, then Cl minus migrate towards AlCl3 and I will get electrophile CH3 plus. So product is going to be methyl benzene or toluene. If this compound is this reagent given CH3 C double bond OCl AlCl3, or they can take acid anhydride also. AlCl3 given, Cl minus bind with the AlCl3, this part become AlCl4 minus, and this will give electrophile CH3 C double bond O plus, and this bind to the benzene ring, and if it is binding to the benzene ring, what product I will get? I am writing here, I will get benzene, this CH3CO plus binding to the benzene structure by replacement of displacement of hydrogen, I will get this compound. If I am taking CH3ClAlCl3 named as the Friedel-Crafts alkylation, if I am taking acid halide AlCl3 or acid anhydride AlCl3, that is known as the Friedel-Crafts acylation. Okay, so these are the main reaction of the aromatic compound. Sometimes they can directly ask question, ki, what is the main reaction of aromatic compound? Now go to the class 12th part. Question is given here, identify all possible monochlorostructural isomers expected to be formed on free radical monochlorination of CH3 CH2 CH3. CH3 twice given here, so CH3 twice, CH given here, CH, the next is a CH2, and this is a CH3. And question is about the monochlorination structural products. For this I'll tell you very simple method, very easy method I'm going to tell you. When they're asking this kind of question, monochloro product, monobromo product, then make different symbols for the different type of hydrogens. For example, you can observe these two CH3 are identical, so I'll draw one identical symbol for both. Here this hydrogen is not matching with these two, means different, I'll make new symbol here. In this case, this CH2 is not matching with anyone, I'll make new symbol here. And this CH3 is also not matching with anyone. Sir, this is CH3, this is also CH3. Yes, this is CH3, this is also CH3. But are they same? Answer is no. You can check this CH3 and this CH3 attached to the CH. This CH3 attached to the CH2. They are not same, they are not identical. So I will make new symbol for this one. Let's say this. So how many different types of symbol are drawn here? These two identical symbol I will consider as 1, 2, 3 and 4. 4 different types of symbols are drawn here, means this can give 4 monochloro structural products on chlorination. Understood the concept or not? Logic is clear to you? Hello. Logic is clear? If they are asking question related to the monochlorination, monobromination, monoiodination of any compound, what to do there? Write the structure of given molecule and just make symbol for different types of hydrogen. Logic is clear? Reply please. Okay, chalo, very good. Next one. Write the product of following reaction. What first compound is given there? First is given there, it is phenyl. I will write like this, PH, CH double bond CH2. What is given here? First is given HBr. Peroxide given here? Sir, no. Peroxide not given. What I said, if peroxide not given, bind bromine to the double bonded carbon having less number of hydrogen. So out of these two, out of CH2 and CH, double bonded carbon, out of CH2 and CH, which one is having less number of hydrogen? Obviously CH here. Am I right? So I will bind bromine to the double bonded carbon having less number of hydrogen. So here I will get PH CHBr CH2. Very simple method na yaar. And assume peroxide given for same. For the same compound they are giving HBr. in the presence of peroxide, then what I said, now I will bind bromine to the double bonded carbon having more number of hydrogen. So this double bonded carbon is having 2H and is having 1H. This has more number of H. So I will bind bromine to this one. I will get pH CH2 Br. Logic is clear or not, bhai? Okay. If HCl given, peroxide given or not given, doesn't matter. In both the cases, bind bromine to the double bonded carbon having less number of H, means Markovnikov, same as HBr without peroxide. Peroxide effect not observed. Peroxide effect is not observed with HCl and HI. Peroxide effect is not observed with HCl and HI. So if HCl is given to me or HI is given to me, I will ignore peroxide effect. For example, here HCl given, now they are giving peroxide or not giving, doesn't matter. I will bind chlorine to the double bonded carbon having less number of hydrogen. Okay, so here 1, 2, 3, 4. You can check this. This is the double. These two are the double bonded carbons. Here, this carbon has only 1H and this has a 2H. I'll bind HCl chlorine to this carbon having less number of H. So I will get this product. If peroxide given for HCl, same answer. Go for the next case. HBr given with the peroxide. Peroxide is important only in case of HBr. Peroxide and HBr given. Go for double bonded carbon. This double bonded carbon has 1H and this double bonded carbon is having 2H. Bind bromine to the double bonded carbon having, please answer, HBr with peroxide given. HBr with peroxide given. I will bind bromine to the double bonded carbon having, answer please, less H or more H. HBr peroxide given. I will bind bromine to the double bonded carbon having less H or more H. Answer please. Very good. And yes, very good. Chalo. So I will bind bromine to the double bonded carbon having more H. So break this pi bond. This is a phenyl. So I can write answer like this. pH. This is CH2. This carbon is, this is CH2. After reaction, this becomes CH2 and CH2Br. Got the concept? Yes. Very good. Means you're not sleeping. What is more important concern here? You are sleeping or not? Okay. Am I teaching very boring? Is it boring? I need to confirm now to know you are sleeping or not. Chalo, very good. What I am observing ki many of you are not sleeping. Okay. Chalo. Next one. It is given haloalkane react with KCN and AgCN. Very important reaction. When AgCl, RCl or RBl, alkyl halide, for example RCl, RBr or RI is treated with the KCN. Two cases are here. One case treated with the KCN and another case treated with the AgCN. If KCN given, major product is nitrile, and if AgCN given, major product is isonitrile. Likewise, we have one more reaction here. RClBr or I, alkyl bromide iodide given, treated with the KNO2, one case, treated with the AgNO2, another case. If KNO2 given, I will get product RONO, and if AgNO2 given, I will get product RNO2. Sir, very confusing. Sir, it is a very confusing. No problem. I will tell you simple trick by which you can find product here. Sir, how? Observe one small thing here. When I am taking Ag, like here Ag taken, then nitrogen is binding to the carbon. This alkyl group has carbon here. Here also you can check Ag and O2 taken. Ag taken, then nitrogen is binding to the carbon. So what I can generalize in these two cases, when Ag taken, when silver taken, like AgCN or AgNO2 taken, then nitrogen, here you can check nitrogen is binding to the carbon. Nitrogen is binding to the carbon. So trick is Agan. You are knowing about the Jagan Mohan Reddy. Now memorize one more, Agan Mohan Reddy. Jagan Mohan Reddy, Agan Mohan Reddy. Am I right? Knowing a Jagan Mohan Reddy? Is there anyone who is not knowing Jagan Mohan Reddy? I think everyone is knowing, am I right? So it is here Agan Mohan Reddy. Means if Ag taken, nitrogen will bind to the carbon. Ag taken, then N bind to the carbon. Ag taken, then N bind to the carbon. So other case you can easily find. Like here, Ag taken, no. So nitrogen is not binding in measure. Carbon is binding. Here, Ag not taken, KNO2 given. Ag not taken, so you can check nitrogen is not binding to the carbon. Actually, oxygen is binding. Got the concept or not? Understood? And why in case of KCN it is predominantly ionic? So in this case AgCN it is predominantly covalent, KNO2 predominantly ionic, and AgNO2 predominantly covalent. Ag cases predominantly covalent, and other cases like sodium potassium cases they are predominantly ionic. Logic is clear, or mainly trick is clear to you or not? So memorize here Agan Mohan Reddy. Next is, in the following halogen, in the following pair of halogen compound, which will undergo SN2 reaction faster? Very important question. I am expecting one question from SN2 this year. These two concepts, what I said just now, this question which I am going to explain, and previous one, I am expecting at least one question from this part. Here, SN2. Always remember, whenever they are asking about the SN2, if steric hindrance is more, SN2 reaction is less. If steric hindrance is more, SN2 reaction is less. Sir, what is steric hindrance? What is steric hindrance? So for steric hindrance, compare me with the Manish sir or AKD sir. Chinna people, AKD sir, Manish sir, they are not giving much hindrance. For example, let's say AKD sir is standing, let's say this is the door. Okay, assume this is the door. This side AKD sir is standing, and this side Manish sir is standing. They are chinna people, okay. So here you can easily go other side, because they will not hinder you. You can easily go inside. Here steric hindrance is low. Now assume another condition. This is the door. One side I am standing. Pedda people, heavy. Other side Panzer. One side VSP sir, other side Panzer. And now you are trying to enter. So very less gap is available here, na yaar. Pedda people. Okay, so here steric hindrance is more. Logic is clear. So big group, big person in terms of height and weight means more hindrance. Chinna people, small people, short people, thin people, steric hindrance less. Small group. Got the concept or not? So check it quickly. In case of first example, you can check. This carbon is given to which chlorine is attached. Here, this side group and this side also, two groups are available. Means two sides are blocked. Here, this chlorine is given, and this is the carbon to which is reacting. Only one group is given here. Here, two sides are blocked. Here, only one side blocked. Where hindrance more? This side hindrance more. Steric hindrance more, SN2 is less. Check it here. One, okay. Out of if it is given RF, RCl, RBr and Ri for SN1, SN2, E1, E2, all cases Ri more reactive, or mainly focus on these three cases RCl, RBr, Ri. If this is given, then Ri more reactive than RBr, RBr more than RCl. Sir, what is the logic here? In Ri it is carbon iodine bond, and in RCl it is carbon chlorine bond. Carbon iodine bond is longer, bond length more, bond energy less. Easy to break. Easy to break means more reactive. So directly memorize SN1, SN2, E1, E2. RCl, RBr, Ri given. Ri more reactive than RBr. RBr is more reactive than RCl. SN1, SN2, E1, E2. Ri more reactive than RBr. RBr more reactive than RCl. So now answer here, in this case, let's say this is compound number 1 and this is compound number 2. Answer, out of 1 and 2, which one is more reactive for SN1, SN2, E1, E2? Answer quickly. Out of 1 and 2, which one is more reactive for SN1, SN2, E1, E2? All 4 reactions you have to answer one thing. Please answer quickly. Out of 1 and 2, who is more reactive for SN1, SN2, E1, E2? Yes, very good. All are giving correct answer. YouTube people, are you sleeping? Okay, I think chat is not live here. Okay, no problem. Chalo. I think you got the answer. Now answer for this also. Okay, the 2 questions were given, discussed. So SN2 reaction, 2 categories: steric hindrance more, reactivity less. Or second case, Ri, RBr, RCl. Ri more reactive than RBr, RBr more reactive than RCl. Next question is about the identify chiral and achiral molecules. You knowing the chiral center. For example, check this carbon. For this carbon, all 4 surrounding atoms or groups are different. For example, here H, CH3, Br, OH. All 4 are different, means this is chiral center. Here, for this carbon, you can check. These 2 are identical. This is not a chiral center. Here, chiral center is not present. In this next case, check this one. For this carbon, it is OH, CH3, CH2, CH2, CH3. All 4 are different. This is chiral center. In this case, check it properly. H and OH, they are different. But this is CH2, CH3. This is also CH2, CH3. CH2, CH3, CH2, CH3. These 2 are identical. This is not having chiral center. Next one also we can check. What is given here? CH3, CBr. If not getting right, this kind of structure will get it. Okay. Check this carbon. CH3, HBr, CH2, CH3. All 4 are different. This is chiral center. Next case you can check. It is given CH3, CH2, 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 Br. You can check for this carbon. Bromine and this thing different. But here 2H, they are identical. It is not having chiral center or chiral carbon. Chalo, next question. Okay, I discuss one concept. In case of aromatic compounds, their main reaction is electrophilic substitution reaction. Electrophilic substitution reaction. Okay, now if chlorobenzene is given, 1 minute. If chlorobenzene is given, okay. Chalo, no problem. I will add here. In case of chlorobenzene, this chlorine is having lone pair. If lone pair containing group is attached to the aromatic ring, it can be chlorine, bromine, iodine, nitrogen, etc. If lone pair containing group is attached, it is having plus M effect and it is going to be ortho para directing. If CH3 present in the place of chlorine, let's say it is CH3. If CH3 present, it is plus H group. It is also ortho-para directing. If groups like NO2, SO3H, SO3H, CN, COOR like this, they are present. They are minus M groups. They are meta directing. Means in this cases electrophile bind at meta. In this case bind either at ortho or at para. And in general para is measure for ortho para directing groups. Here what is given to us? Chlorobenzene is given. In this case what is given to us? Chlorobenzene is given. So in case of chlorobenzene, this chlorine is containing lone pair, means it is plus M, means it is ortho para directing. It will say to electrophile bind at either ortho or at para, and para is going to measure product in this example for all ESR reactions. So for example, let's say Cl2, Al, Cl3 or FeCl3 given. This will generate electrophile Cl plus. That's what we discussed few minutes back only. And since this chlorine which is already present in the ring is ortho-para directing, so this chlorine will also bind at ortho or para. Here para will be major and ortho is going to be minor product. Logic is clear, and if you knowing this, you can solve all the reactions. Please observe one by one. Second case, what is given? HNO3, H2SO4 given. Nitrating mixture is given. This will generate electrophile NO2 plus. What is the behavior of chlorine? This chlorine which is attached to the aromatic ring is ortho-para directing. So this NO2 plus bind at ortho, one possibility, bind at para, another possibility. Para is major, ortho is minor. Go to the next example. Concentrated sulfuric acid given. It is giving electrophile SO3 and product is going to have SO3H. Chlorine is ortho-para directing, SO3H and SO3H you can check. It is para-chlorobenzene sulfonic acid and this is ortho-benzene sulfonic acid and para is major. Next reaction, next Friedel-Crafts reaction. What is given here? CH3, Cl, Al, Cl3. I said one simple logic. CH3, Cl, Al, Cl3 given. Cl minus move towards Al, Cl3. This will generate electrophile CH3 plus. This will generate electrophile CH3 plus. Okay. Now you are knowing concept. Chlorine is ortho-para directing. So one product CH3 present at ortho, one position CH3 present at para, para major, ortho minor. Okay, chalo. Next example, what is given? CH3, CO, Cl3 given. What will happen? Cl minus move towards Al, Cl3. So this part will come out as Al, Cl4 minus, which will later on recover as Al, Cl3. And this will give electrophile CH3, C double bond O plus. Now chlorine is ortho-para directing. So this group can bind at para position of chlorine, one possibility. And this group can bind at ortho position of chlorine, another possibility. Para is major, ortho is minor. Are you knowing ortho-para concept? If someone is not knowing what is ortho-para meta, so I'll tell you here. Let's say any group is attached here, any group G is attached here. Then these two carbons are ortho. These two are meta. And this one is a para. Okay. For example, this is given. So in this case, these two are ortho, these two are meta, and this one is para. Means opposite to the group is para. These two are ortho and this is meta. Okay. Chalo. Next one. Give IUPAC name of the following compound. This is given for practice. Because concept related to the IUPAC nomenclature I already discussed. You have to solve it, okay? So consider this as homework. Consider this as homework, okay? This is taken here for the revision purpose. In the revision also revision. Okay? This is homework question for you. Next one. Give the structures and IUPAC name of the product expected from the following reactions. First is given catalytic reduction of butanol. Al is written. Al means aldehyde. Al means aldehyde. Butanol means I have to make aldehyde of 4 carbons. Butanol. What is given as catalytic reduction? Catalytic reduction means reaction of the compound with hydrogen in the presence of catalyst like Ni, Pd or Pd. In this case, for this C double bond O, pi bond break and hydrogen bind here. So it is going to be, I am not writing hydrogens attached to the carbon. So 1, 2, 3, 4. And when this pi bond break and 1 H bind to the oxygen and 1 H bind to this carbon, here I will get this CH2OH. Other hydrogens are not represented. Means it become butane 1-ol or butane 1-butanol. Okay. Got the concept? Next is given there hydration of propene in the presence of dilute sulfuric acid. What is given? Propene is given. Propene. So write on structure. Propene CH3CH double bond CH2. What is given? Hydration. Dilute sulfuric acid given. Dilute sulfuric acid given. Means large amount of water and a small amount of sulfuric acid. So here I can write this as H2OH plus also. Trick is very simple. I am not saying the mechanism here. It is a trick only. Trick is very simple. H2O given, you can write this as H plus and OH minus. It is not the reality. It is only a trick. Then apply the concept what I said for the HBr. Now in this case, in case of HBr, H is plus and Br is minus. In case of HCl, H is plus, Cl is minus. In case of HI, H is plus and I is minus. What I said, if these type of cases given, bind bromine, chlorine, iodine to the carbon having less number of hydrogen. Here, trick is very simple. H2O, H plus is given or dilute sulfuric acid given means consider H2H plus because dilute sulfuric acid means large amount of water, small amount of H plus or acid. So trick is very simple. Write H plus and OH minus. So minus part is OH here. Minus part is OH. This is only trick, not reality. Now, out of these two carbon, double bonded carbons, which one is having less number of H? Sir, this is having less number of H. So bind OH to the carbon having less number of hydrogen. Trick, understood the concept? So I will bind this OH to the carbon having less number of hydrogen. I will get propane 2-ol. Propane 2-ol. Next is given there reaction of propanone with methyl magnesium bromide. What is given there? Propanone. On means ketone. Pro means 3 carbons and on means ketone. I have to attach double bond here, double bond O here. If I attach double bond O to the terminal here, it become aldehyde. Al. It is on. So double bond attach here. Next is given methyl magnesium bromide. Methyl CH3MgBr. So in the beginning only, I said one concept to you. Here, if metal and carbon given, metal will acquire plus and carbon will acquire minus. Magnesium is metal. So metal is plus, carbon is minus. In this C double bond O, who is more electronegative? Sir, oxygen. So oxygen is minus and carbon is plus. And you're knowing from class 6th, 7th or below also that plus minus charges are attracting each other. So this minus is going to bind with the plus. Obviously minus bind with the plus and plus bind with the minus. So minus bind with the plus, this pi bond will break, it become O minus. O minus bind with the plus. So here I will get, see, you can easily understand here. I am not representing hydrogens, okay. So here, this CH3 bind to this carbon, this is CH3 binding to this carbon, and when pi bond break, this become O minus, minus bind with the plus. Who is plus here? MgBr. It is going to be MgBr here. If water is added, water as per trick, I can write H plus and OH minus. Then same point here also, O is minus, minus bind with the plus. Who is plus here? H plus. So I will get this compound CH3. I can write like this also, just for representation. I'll get this compound. Okay. Next is given, arrange the following compounds in the order of their boiling point. First is given pentane 1-ol, 1, 2, 3, pentane 1, 2, 3, 4, 5, 1-ol, pentane 1-ol, pentane 1-ol. Next is given butane 2-ol, 1, 2, 3, ethanol 1, 2, propane-ol 1, 2, 3, and methanol, this one 1, 2, 3, 4, and 5. All are alcohols. All are alcohols. So if same kind of molecules are given, like all are monohydrate alcohol, one OH present everywhere, then you can check the size of molecule. Out of all 5 molecules, which one is biggest here? So answer is 1. It is having 1, 2, 3, 4, 5 carbons. Biggest molecule, more surface area. So boiling point of 1 is maximum. Then this 4 carbon 2. Then 3 carbons here, number 4. Then 2 carbons here, number 3. And then this number 5. Okay. So this is big, and this one is very small. If surface area more, interaction more, boiling point more. For the same kind of molecules, like here all are having 1 OH group. Okay. If alcohol versus alkane or ether given of comparable molecular masses, then you are knowing alcohol is having hydrogen bonding, they don't have. So boiling point of alcohol is more than alkane or ether if molecular masses are almost equal. If molecular masses are almost equal. I'll tell you one simple concept here. Boiling point, carboxylic acids are having more boiling point than alcohols. Alcohols are having more boiling point than aldehydes or ketones. And they are having more boiling point than alkanes or ethers, provided their molecular masses are comparable. Comparable means either exactly equal or almost equal. By this logic, you can solve many problems. Carboxylic acid, alcohol, aldehyde, ketone, and then alkane or ether, provided molecular masses are comparable. Next is about the acidity of alcohol. Acidity of alcohol. So always remember, this is a primary alcohol, secondary and tertiary alcohols are given. So always remember, presence of plus I, plus M or plus H is going to decrease the acidic strength, and presence of minus M, minus I or minus H is going to increase the acidic strength. Here this R is a plus I. Alkyl group is plus I. Alkyl group plus I. Okay. Here 2 plus I. And here 3R means 3 plus I. What I am knowing? Plus I will decrease acidic strength. So here acidic strength decrease by 1 plus I. Here acidic strength decrease by 2 plus I. And here acidic strength decrease by 3 plus I. So who is going to be more acidic? Answer is primary, then secondary, and then tertiary. Okay, logic is clear. So presence of plus I, plus M or plus H will decrease acidic strength. Presence of minus I, minus H or minus M will increase the acidic strength. Next example. Acidic strength of mononitrophenol. This is very important. Very important. Acidic strength of mononitrophenols. Here OH is given. This is orthonitrophenol, metanitrophenol, paranitrophenol, and phenol. If they are asking acidic, this is orthonitrophenol, this is metanitrophenol, this is paranitrophenol, and this is simply phenol. Okay. So if they are asking acidic strength order of the mononitrophenols, if they are asking acidic strength order of mononitrophenols, directly memorized by the trick, and that is a POM phenol. POM phenol. What is the trick here? Pom phenol, POM, pom phenol, like mom pom, mom pom. Para nitrophenol is more than orthonitrophenol. Orthonitrophenol is more than metanitrophenol, and metanitrophenol is more than phenol. This is the order of acidic strength. Don't forget, this is the order of acidic strength. If acidic strength more, pKa value is less. Sometimes they can ask pK value also. So if mononitrophenols are given, directly go for the acidic strength by this trick, pom phenol, para-nitrophenol, orthonitrophenol, metanitrophenol, and then phenol. Okay or not? If they are asking pKa order, it is going to be reverse. Okay or not? Very important concept is here. Okay. Chalo, move to the next question. Here they are asking, the following is not an appropriate reaction for the preparation of tert-butyl ethyl ether. Tert-butyl ethyl ether. So one side tert-butyl group and other side ethyl group. This is tert-butyl ethyl ether. So always remember one concept. If you are reacting RO minus with the alkyl halide and you want to make ether, then this alkyl halide should be primary. Then O minus attack on this R, X will leave. If you want to make ether, by using RO minus reagent, then alkyl halide must be primary. It is a part of Williamson's ether synthesis. For this also we have trick. Don't worry. Listen properly. Check the name. William. I will treat this as 1. William is repeatedly saying, use 1 degree alkyl halide. William is repeatedly saying, use 1 degree alkyl halide. Sir, for which purpose? For ether synthesis. William, name is saying. Name is giving answer. Name is Williamson's ether synthesis. William, name is saying 1 degree. Many times he is saying 1 degree. Who is 1 degree? Alkyl halide. Take 1 degree alkyl halide for ether synthesis. Logic is clear. Chalo, very good. So now check this reaction. Here C2H5ONA given. So I can write this as C2H5ONA given. So I can write this as C2H5O minus. Any problem? Check. This carbon is a 3 degree carbon, means this is 3 degree alkyl halide. What William is saying, if you want to make ether, this is ether na yaar. This is ether. What William is saying, if you want to make ether, take 1 degree alkyl halide. What is taken here? 3 degree. So is it appropriate method for this ether? Answer is no. Then how I can make? Concept is same. It is there in front of you only. If you want to go for Williamson's ether synthesis, take 1 degree alkyl halide. Here it is 3 degree alkyl halide. I cannot go for ether synthesis. Am I clear to you? Are answer yaar. Please answer. Hello. Please wake up. Chalo. Okay. Very good. So here, why this is not good for ether synthesis? Because alkyl halide is a tertiary. What to take? A primary. So now I want to make this ether. I want to make this ether. I will tell you 2 conditions. You have to answer which one is correct. First condition, this is taken and this is taken. Second condition, this RO minus taken and this alkyl had taken. Let's say this is condition number 1, condition number 2. Answer, which one will give me ether? Which one will give me ether? 1 or 2? 1 or 2? Answer quickly. Audio is coming or not? Are audio coming or not? Birmani sir came. Okay. Chalo. Okay. Now this is given. Which one will give ether? Yes, all are giving correct answer. All are giving what, sir? हो जाएगा ना? Yeah. Thanks, bro. Chalo. Okay. So here, in which case alkyl halide is a primary? In this case, sir, this is a primary alkyl halide. Here I will get this ether. Logic is clear. If it is secondary tertiary, then alkene will form. For example, here chlorine leaving group alpha beta. This is beta hydrogen. In case of tertiary or in fact of secondary also, this RO minus will remove beta hydrogen. RO minus will remove beta hydrogen. Sigma will hit here. Cl will leave, and this will give us alkene. You can check here. Double bond formed here. So carbon carbon double bond. Here it is carbon carbon double bond, and this alkene will form in this second case. Chalo. So Williamson's ether synthesis is also covered. Chalo. Next and last reaction for the ether chapter. In case of ethers, when they are giving this kind of reaction, they can give here HI or HBr. HI or HBr. Method is a very simple method. Check it here. First is H plus I minus. Bind H plus to the oxygen. I will get this oxonium ion of ether. Left hand side is 3, right hand side is 1 degree. 3 degree is preferring SN1, 1 degree preferring SN2. If this situation is there and SN1 is preferred, SN1 versus SN2 in the same, SN1 is preferred. And SN1 means make carbocation. So I will break this bond because I want to make carbocation towards 3 degree. So this bond I will break. So this part will give me carbocation. That is a CH3 thrice C plus. So obviously this OH will go with this part. And this part is going to be CH3OH. And here carbon is plus is given. Bind with the I minus. And this will give me CH3 thrice Ci third butyl iodide. Understood or not? Are answer please. Understood or not? Are clear na bhai? Clear or not? Chalo. Very good. So this alcohol, phenol, ether chapter also over. Move to the. Okay. Here one very important question given. After that we'll move to the next chapter. Okay, this is also part of the next chapter actually, aldehyde, ketone and carboxylic acid. Here through this question, we'll discuss all important reagents. First is given hexane 1-ol to the hexenal. Ol to ul. Ol means alcohol, ul means aldehyde. ठीक है? Hexane 1-ol. 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It is ol at one position. Hexane 1-ol. 1, 2, 3, 4, 5, 6. It is ol, 1-ol. Okay, hexane 1-ol, obviously. And from this we have to make aldehyde 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And from this we have to make here aldehyde. Focus on the functional group. It is alcohol, primary alcohol, and from this I have to make aldehyde. Alcohol to aldehyde is oxidation. Alcohol to aldehyde is oxidation. When you want to oxidize primary alcohol into the aldehyde, you have to use mild oxidizing agent. What to use? Mild oxidizing agent. Sir, why? If you're taking a strong oxidizing agent, then this will oxidize up to the carboxylic acid. This reaction will not stop at aldehyde. If a strong oxidizing agent taken, then reaction will not stop at aldehyde. This aldehyde will oxidize further into the carboxylic acid. I'll come to that also. Okay. So if mild oxidizing agent taken, then this primary alcohol will give us aldehyde. Oxidizing agent for this conversion as per our syllabus, one is PCC, pyridinium chlorochromate. Pyridinium chlorochromate. Very easy to memorize formula and structure also. Pyridine molecule you are knowing, this is pyridine molecule, but name is pyridinium. Bind 1H become pyridinium. Next is even chlorochromate. Chlorochromate. So chromium. Chloro term is given. So one chlorine and other places with oxygen. Okay, so it is chlorochromate. This is a pyridinium chlorochromate, mild oxidizing agent. You can check formula also written there. This part written here, C5H5NH plus CrO3Cl minus. CrO3Cl minus. Okay, now pyridinium chlorochromate. This will convert primary alcohol into the aldehyde. Or we can take one more, CrO3 anhydrous. CrO3 anhydrous without water. CrO3 without water. Sir, what if strong oxidizing isn't taken? So assume this primary alcohol is treated with some strong oxidizing agent like KMnO4, K2Cr2O7, H2CrO4, chromic acid. In these cases, this will oxidize. Total carbon 1 to 6 carbon 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This will oxidize into carboxylic acid. Carboxylic acid. If strong oxidizing isn't taken, this primary alcohol will oxidize into the carboxylic acid. Chalo, very good. Understood the concept? Understood the concept or not? This conversion, primary alcohol to aldehyde is possible by giving copper or silver at 300 degrees Celsius also, provided given alcohol is volatile. Chalo, next one. Next given cyclohexanol. Cyclohexanol. This is cyclohexanol. 2-cyclohexanone. Now if you are making, this is secondary alcohol, and from this you are making this ketone. Here I can use mild oxidizing agent as well as strong oxidizing agent. If you are using strong oxidizing agent, avoid heat. Otherwise, ketone will also oxidize by carbon-carbon bond break. Previously, same I can use here. Here important point is, if I'm making ketone from the secondary alcohol, you can use a mild oxidizing agent as well as strong. If strong is used, don't heat or don't go for strong heating, otherwise formed ketone will also oxidize. Chalo, next is given there 1-fluorotoluene, 2-fluorobenzaldehyde. Okay, so I'll tell you one important reaction here, very important reaction, very important reaction. We have here methyl benzene. In this methyl benzene we can attach any group, nitro, fluoro, any group, whatever you want attach, no problem. And I want to convert this methyl CH3 group into CHO group. I want to stop reaction at aldehyde. Is it possible by strong oxidizing agent? Answer please. I want to stop reaction at aldehyde. Is it possible by strong oxidizing agent? Is it possible by strong oxidizing agent? Yes, not possible. Very good. Chalo. So here three methods are there. One is a CrO2Cl2 in carbon disulfide followed by hydrolysis, named as retard reaction. Or another method is we can go for CrO3 acetic anhydride, CH3 C double bond O, C double bond O, CH3 followed by hydrolysis. One more is there. Firstly give Cl2 in the presence of light and then go for the heating with water at 100 degrees Celsius. This is the commercial, this is the industrial method of conversion of this methyl benzene to the benzaldehyde. So here what I am taking, CrO2 Cl2 in CH2, no water, water not taken. It become mild oxidizing condition, reaction will stop at aldehyde. Here you can check CrO3 acetic anhydride taken. Acetic anhydride taken without water. Here also water not taken. It become mild condition, reaction will stop at aldehyde. Now this is sir water to added. Yes, I am adding water once this first reaction is over. Oxidizing agent reaction is over. Then I am adding water. Na? So how to recognize in exam? How to recognize in exam? In case of one, in case of this case, in this case, observe please. What is taken here? CH2 taken, water not taken. Oxidizing action is not very high. Reaction will stop at aldehyde. Here also water not taken. Means oxidizing action is not very high. Reaction will stop at aldehyde. Okay, and this is third, Cl2H nu given, followed by addition of water, vapor, it is giving aldehyde. This is the industrial method. Okay, so all important reaction related to the conversion of different compound with aldehyde discussed here. Okay. Next given ethane nitrile. Nitrile, I will tell you simple method. If nitrile given, and I want to make aldehyde, then I can use a diol H followed by hydrolysis. In the place of diol H, I can use SnCl2HCl also. Okay, chalo, very good. I will tell you one more small concept here that is very important, and I am expecting one question from this part also. Let's say carbon-carbon double bond is given. Carbon-carbon double bond given. For example, this molecule is given. And now they are giving you O3, ozone, followed by H2O in the presence of zinc dust. This is named as ozonolysis. This is named as ozonolysis. If this condition is given to you, method is very simple. Break this double bond, bind one oxygen to this carbon and one oxygen to this carbon. Break double bond, bind one oxygen to this one to another. So if I bind oxygen here, this part become R C double bond OH, and right side part become R C double bond OR. This is ozonolysis. Okay, chalo. Next one. These reactions which are given here, very easy reaction. Even class 8th, 9th students can also solve. Observe this compound given, and this is known as 2,4-dinitrophenyl hydrazine, 2,4-DNP. What is the concept here? This O and this NH2, means take NH2 and this O, remove water. This will be removed as water. So N bind with the carbon through double bond. I'll get this compound. This is colored. So 2,4-DNP is used in the identification of aldehydes and ketones. Okay. Next reaction. Observe this thing. Whenever you have this condition, CH3, C double bond O, this side R, H or PH. Or we can have this condition, CH3, CHOH, R, H or PH. And if halogen with base given, or they can give NaOX also. In this case, CH3 attached to the CHOH or CH3 attached to C double bond O converted into halo form CHX3. So what is the important concept here? You can check CH3 attached to the C double bond O, halogen with base given. So the CH3 part will become CHX3 here, iodine given, so CHI3. And remaining part will come out as carboxylate. Okay, logic is clear. Logic is clear. Chalo, very good, very good. Okay, next one. See, this is discussed previously. You can check. It is a primary alcohol. What is it? CrO3 with sulfuric acid. Sulfuric acid is dissolved in water. So CrO3 given and sulfuric acid dissolved in water. Water present means this is going to act as a strong oxidizing agent. If it is acting as a strong oxidizing agent, primary alcohol will oxidize into carboxylic acid. This is also named as Jones reagent. Chalo. Very easy question. What is given here? C6H5CH2OH. HBr given. So here H plus Br minus. So I will write here C6H5. I can write like this: PH CH2OH and HBr given. What will happen? This part will come out as water. Then bromine bind to this carbon. I will get here PHCH2Br. PHCH2Br. Logic is clear. So in this reaction, what is happening? This H and OH coming out as water. I get this compound. KCN given, we discussed earlier. KCN given, then who will bind? CN. AgCN given, who will bind? NC. CN. And in case of CN, many important reactions are available. In case of CN, many important reactions are available. For example, if it is going for hydrolysis, which is partial, it is giving amide RCONH2. And if it is going for complete hydrolysis, water heating given, it will give carboxylic acid. Now here, what is formed? CN is formed. What is given there? H3O heating, complete hydrolysis. Complete hydrolysis of CN will give carboxylic acid. Remember directly, partial hydrolysis of CN will give amide. Partial hydrolysis of CN will give amide, and complete hydrolysis of CN will give carboxylic acid. Complete hydrolysis will give carboxylic acid. Chalo. Move to the next. Very easy reaction. Very easy reaction. And this we discussed earlier also. This compound is given. I'll tell you by simple example here, and then later you can solve this one. I'll give you concept and you can solve this reaction by using this concept. PHBr magnesium diether given. Alkyl halide magnesium given, Mg, it is Mg, magnesium. Alkyl halide magnesium given. Then magnesium is going between pH and Br, it becomes PHMgBr. Phenyl magnesium bromide. Okay, what next given there? CO2 given. So I will write structure here. In organic chemistry, if you're writing structure, solving problem become very easy. Like in physics, what they are saying, make diagram, question become easy. Like you're not drawing free body diagram, etc. Am I right? In physics, make diagram, it become easy problem. In organic chemistry, make structure of the molecule, it become easy concept. It become very easy, okay. So here, PHMgBr, from beginning we are knowing one concept. If metal, not necessarily magnesium, metal is attached to the carbon. If metal is attached to the carbon, like here magnesium metal attached to the pH carbon, then magnesium metal will acquire plus and pH will acquire minus. Carbon will acquire minus. Simple. In this carbon dioxide, out of carbon and oxygen, who is more electronegative? In this carbon dioxide, out of carbon and oxygen, who is more electronegative? Answer please. In this carbon dioxide, out of carbon and oxygen, who is more electronegative? So oxygen will be delta minus or delta plus? Oxygen will be delta minus or delta plus? Oxygen will be delta minus or delta plus? And carbon delta plus. Very good. Chalo. So here carbon will be delta plus, oxygen delta minus. Then it is class 6th, 7th concept. Minus bind with the plus. So this pH is minus and this carbon is plus. Minus bind with the plus. Pi bond break, it become O minus. This O minus bind with the plus. Who is plus here? MgBr. So what I will get this? Observe, this pH is binding to this carbon. This double bond O not changing. Pi bond break, this become O minus. Bind with the plus MgBr. Now if I add H plus here, acid, this is O minus. Minus bind with the plus. So O minus bind with the H plus. So when O minus bind with the H plus, I will get here pH, C double bond O. See, this is O minus bind with the H plus, it become OH. Understood? And knowing solid CO2 is also named as dry ice. Chalo, next question. This is discussed previously. Check it. What is given here? KMnO4 KOH. Obviously heating is required here. It is a strong oxidizing agent or mild. KMnO4 KOH, strong or mild? Strong or mild? Answer please. Strong or mild? Strong. Chalo, very good. So reaction will go up to aldehyde or carboxylic acid? Yeah, all are correct. Strong, very good. So reaction will go up to aldehyde or carboxylic acid? Aldehyde or carboxylic acid? Answer please. Yes, very good. Chalo. So strong oxidizing agent given. So this carbon become carboxylic acid and this carbon also become carboxylic acid. Here we have one concept. If it is alkyl group, at least one hydrogen must be attached to the carbon, which is directly attached to the benzene. Means at least one hydrogen must be here. Means at least one alpha H must be present. Since medium is basic here, so firstly it will be COO minus K plus and COO minus K plus. When I add H plus, CO minus become COH and this CO minus also become COH. This is easy concept. What is important point here? Strong oxidizing agent given. So this CH3 will oxidize into COOH and this ketone will also oxidize. Ketone or CH3 attached to the benzene ring will oxidize into the carboxylic acid if a strong oxidizing agent is given with heating. In question part, heating was discussed. Okay, so heating is mandatory here because I am converting ketone into the carboxylic acid. If I don't heat, ketone will not become carboxylic acid. Aldehyde become carboxylic acid by strong oxidizing agent without heat. Chalo, next one. Very easy question. Again, answer please. Strong oxidizing agent given or mild? Strong or mild? Please answer. Strong or mild? Are answer yaar? Yes. So what will happen? This bond will break. Double bond, carbon double bond will break. Okay, and by breaking I will bind oxygen here and here. So how many carbons are there? 1 2 3 4 5 and 6. So 1 2 3 4 5 6. 1 2 3 4 5 6. So this carbon is getting one oxygen, so this become double bond O H initially, and this is also going to become double bond OH initially. But it is a strong oxidizing agent, na? So can we stop reaction at aldehyde? Can we stop this reaction at aldehyde? Can we stop this reaction at aldehyde? Can we stop this reaction? Yes. No, no, no. Very good, very good. So this will become OH carboxylic acid, and this also become OH carboxylic acid. Okay. If condition is given ozone followed by H2O zinc, then this bond will break, bind oxygen, oxygen. So 1, 2, 3, 4, 5, 6. Here double bond OH, double bond OH. Here reaction will stop at aldehyde. Ozone H2O zinc given, reaction will stop at aldehyde. But if strong oxidizing agent given, reaction will not stop at aldehyde. Aldehyde will oxidize into carboxylic acid. Here also carboxylic acid. That's why you can check here, it is giving dicarboxylic acid. Okay, okay, okay. Chalo, next one. Okay, this I will discuss in the test of functional parts. So I'm leaving for now. It will be discussed. One concept I said earlier, if you go into attach electron with the drawing group, for example, -I, it will increase acidic strength. If you are binding electron donating group, for example, +I, this will decrease acidic strength. Electron with the drawing group increases the acidic strength of given acid by stabilizing its conjugate base. +I, electron donating will decrease acidic strength. That's what they are writing here. Electron with drawing group stabilizes the carboxylate ion and strengthens the acid. Electron donating group destabilizes the carboxylate ion and weakens the acid. Very simple, plain and simple concept. -I, -M, -H, they will increase acidic strength. +I, +M, +H, they will decrease acidic strength. Okay. If confusion is coming, very easy. Acidic strength A minus will increase AS. -I, -H, -M will increase acidic strength. Okay, by this you can memorize it. -I, -H, -M will increase acidic strength means electron with the drawing group. Understood now? How to memorize? A is a minus will help in the acidic strength. Chalo. For example, these three compounds given here. NO2 is -M. NO2 is -M. OCH3 is +M. So -M will increase acidic strength. So compound number 1, 2, 3 given. All three are benzoic acid. Functional groups are same. -M will increase acidic strength and +M will decrease acidic strength. So out of 1, 2, 3, who is the most acidic? Answer is 3 is acidic strength. I am writing order of acidic strength. 3 is more acidic. Then see, in 1 it is decreased by +M. So 1 is going to be less than 2. So 3 is more than 2 and then 1. If acidic strength more, pK value less. You can check pK value is less here, 3.41. If acidic strength is less, pK value more, you can check it is more here. So if they are asking pK order, it is the reverse of the acidic strength. And last concept of this chapter, aldehyde, ketone, carboxylic acid uses. They can ask directly one question from the uses. I am expecting one question from this part. Okay. Very important points are written here. Memorize all the points given. Here. For example, hexane dioic acid is used in the manufacturing of nylon 6,6. Okay. You knowing this molecule CH3COH acetic acid is used as vinegar in the food industry. Esters of benzoic acids are used in perfume. You have to know one concept. Esters are having sweet smell, sweet fruity smell. Okay, so ester of benzoic acid are used in perfumery. Obviously, if it is having sweet smell, fruit like smell is there, I can use that one as a perfume. That's why they're adding here, ester of benzoic acid are used in perfumery. Next, and very important point, sodium benzoate is used as a food preservative. Nowadays, many packed food are coming, like buy today, eat after 3 months, eat after 2 months. So something is required there to preserve it for longer period of time. So there we are adding food preservatives. One of them is given here, sodium benzoate. And last one, higher fatty acids are used in the manufacturing of soap and detergent, like large carbon chain carboxylic acid. The sodium or sodium salt or potassium salt can be used in the manufacturing of soap and detergent. So when you're using some soap or detergent, it may be large fatty acid. Okay, long chain containing carboxylic acid is fatty acid. Move to the next chapter and last chapter of the organic chemistry. Okay, amines. Classify the amines as primary, secondary or tertiary. Classify amines as primary, secondary or tertiary. Okay, chalo. Very easy question. I'll tell you one simple method. Very easy method. If you have NH2, it is a primary amine. If you have NH, it is a secondary amine. This side it can be R or pH. R or pH. This side also it can be R or pH. If you have N, this side can be R or pH, R or pH, R or pH. It is a 3-degree amine. Okay or not? ठीक है, got it. So now answer. What about first? And if it is aromatic ring, I will name it as aromatic amine. If it is aliphatic ring, aliphatic compound, aliphatic group attached there, I will name it as aliphatic amine. Like if R attached, aliphatic primary amine, pH attached, aromatic primary amine. Similarly, this all and this also. So now answer. What about first compound? Primary, secondary or tertiary? अरे आंसर भाई, primary, secondary or tertiary? Please answer. Otherwise, this time I will sleep. Quick. I want quick reply. Yes. Answer quickly. Primary, secondary or tertiary? Primary. Very good. All are giving correct answer. Aromatic or aliphatic? Answer this also. Aromatic or aliphatic? Aromatic or aliphatic? अरे आंसर यार. चलो. Very good. Chalo. Okay. Yes. This is a primary amine. What about the next one? Primary, secondary or tertiary? What you are able to find there? N. What you are able to find there? N, NH or NH2? N, NH or NH2? What is there? N, NH or NH2? N, NH or NH2? What is present there? Yes. All are giving correct answer. This is a 3-degree or tertiary amine. Chalo, very good. What about next? I am writing structure also. C2H5 twice CHNH2 given. Okay. So I will write structure here. C2H5 CHNH2 C2H5. Now answer. Primary, secondary or tertiary amine? Please answer. Yes, yes, primary. Very good, very good, very good. Here it is NH2 primary. Okay. Last example. Yes, this one. Number 4. Number 4. Number 4. Last one. Number 4. Quick. I want quick response. Yes, very good, very good. All are correct. Chalo, chalo, good, good, good. Next one. Write the chemical equation for the following reaction. C2H5Cl with the ethanolic ammonia. Very easy concept. What is given? C2H5Cl. C2H5Cl, I will write like this. CH3. CH2Cl reacting with the ethanolic ammonia. Here ethanol is a solvent, okay. Reaction performed in a sealed tube at 100 degrees Celsius. Now here, this nitrogen is containing lone pairs will act as nucleophile. This carbon is delta plus will attack on this carbon, Cl will leave. Cl is coming out as Cl minus here. Cl is coming out as a Cl minus. So we'll take one hydrogen from here. So Cl minus and one H plus from this NH3 will come out as a Cl. So here I will get CH3, CH2, NH2. Sir, why NH2 is coming here? I am repeating again, listen it properly. So it will help to understand the next part of reaction. This NH3 attack on this carbon, Cl is coming out. Cl is coming out as a Cl minus. Since it is coming out as a Cl minus, we'll take H from this NH3. So one H is taken by Cl minus, coming out as a Cl. So what left here? NH2. Now, this will react with another molecule of CH3, CH2Cl. So this nitrogen will attack on this carbon, Cl will leave. Same point here also. Cl minus will take one hydrogen from here, come out as HCl. What I will get? CH3, CH2, NH, CH2, CH3. Then this can react with next molecule of CH3, CH2Cl. So what will now happen? This nitrogen is having lone pair, attack on this carbon, Cl will leave. Same, actually I'm repeating the same concept, okay. Cl is coming out as a Cl minus, will take H plus from here, come out as HCl. So this will give us here CH3, CH2N, CH2CH3, and it is a CH2CH3. And if one more CH3CH2Cl given, then this nitrogen will attack on this carbon and Cl will come out. This time there is no hydrogen attached to this nitrogen to come out as HCl. So this C2H5 or CH3CH2 bind to the nitrogen and there is no H to come out as HCl. So here I will get here CH3, CH2. How many? 1, 2, 3 and this one also. So 4 N plus and Cl minus. Means this reaction is named as a monolysis. It means this reaction is giving me here. This reaction is giving me here primary amine, secondary, tertiary amine and quaternary ammonium salt. This is known as a monolysis. Okay. ठीक है, समझ गए? Understood? Okay. चलो, okay. So with the same logic, we can solve both the questions what I said to you. Next, how will you convert benzene into aniline? Benzene into aniline. Very good question. Benzene is given and you have to make aniline. Benzene is given and you have to make aniline. So first of all, I'll go for the nitration reaction. For nitration, what we are using? Nitric acid, sulfuric acid mixture. named as nitrating mixture. By this reaction I will get nitrobenzene. Now if I want to reduce this NO2 group into NH2 group, then I can use H2 palladium in the presence of ethanol solvent, or I can use FeSCl, or I can use SnSCl, metal plus HCl. Okay, FeSCl is preferred. Okay, got the concept now? This is how we can convert benzene into aniline. Second given there, benzene into NN dimethyl aniline. So start from benzene, and what to make there? NN dimethyl aniline. So what is aniline? This is aniline molecule. But what is given there? NN dimethyl aniline. Means here methyl group is attached to the nitrogen, and how many? 2. NN dimethyl aniline. So firstly make aniline from the benzene. How it is possible? Just now I said, so I will write directly here. First give nitrating mixture HNO3 plus H2SO4. This will convert benzene into nitrobenzene, and then give FeSCl and other reagents also available. You will get this aniline. But what to bind now? CH3. 2 CH3 I have to bind to this nitrogen. If I want to bind CH3, I will give CH3X, for example CH3Cl, CH3Br, or CH3I. Logic is discussed few minutes back only. This nitrogen attack on this CH3, Cl will leave. Cl minus and this H plus come out as HCl. So if I am giving one equivalent of CH3Cl, here I will get NHCH3. It is N-methylaniline, but I want to bind one more CH3 there. So I'll give one more equivalent of CH3Cl. Sir, what will happen now? This nitrogen will attack on this CH3, Cl will leave. Cl coming out as Cl minus. We'll take this hydrogen, so Cl minus and this H come out as HCl, and this CH3 bind to the nitrogen. I'll get desired product NN dimethyl aniline. It is a very important question. From here also I'm expecting one question this year. Chalo, next one. Order of basic strength of ethyl and methyl amines. Very important. Very easy trick is there. If they're asking basic strength of methyl or ethyl in aqueous solution, in aqueous medium, then we have two numbers here, 213 and 231. 213 and 231. 213, 231. 213, 231. If it is methyl group present, two cases I am discussing here, methyl and ethyl cases of the amines. Very easy trick is available to find the basic strength in water, in aqueous medium. Very easy trick is available. Out of 213 and 231, which number is smaller? Out of 213 and 231, which number is smaller? This you can answer here. Out of 213 and 231, yes, very good, 213 is smaller. And out of CH3 and C2H5, which one is smaller? Out of CH3 and C2H5, which one is smaller? CH3. So match smaller is smaller. A small group, small number, match them. Big group, big number, match them. Means this is only for basic strength in aqueous medium. Basic is in aqueous medium. If they are asking in gas phase, basic strength in gas phase, then 3 degree, 2 degree, 1 degree alkyl amine followed by ammonia. Means R3N more than R2NH more than RNH2 and then ammonia. Gas phase 3 to 1. This 213, 231 is only for basic strength in aqueous medium. अरे ठीक है बोलो. Understood? So now if it is ethyl, trick is what? If they're asking basic strength in aqueous medium, then two numbers are there, 213, 231. 213, 231. Small number, small group. Big number, big group. Only for aqueous medium. Gas phase 3 to 1 for all alkyl amines. Chalo, theek hai, so you can find answer now. Now check it. If it is methyl, you can check it. It's CH3 twice NH, 2. Then only one CH3 present here, 1 degree. Then 3, 2, 1, 3, and then ammonia. In case of ethyl, C2H5, 2, then 3, and then 1 ethyl, 1, and then ammonia. And they can ask, this is the order of basic strength in aqueous medium. If they are asked pKb, so basic strength more, pKb less. So pKb order will be reverse of the basic strength. If nothing is given by them, consider aqueous medium. Okay, chalo, very good. Next question. Here what is given? Br2 given in the presence of some Lewis acid, for example, let's say FeBr3. This will give me electrophile Br plus. CH3 is ortho-para-directing. CH3 is ortho-para-directing and activating. NO2 is minus M, it is deactivating. If activating and deactivating both are present together, then go according to the activating. So CH3 is activating, I will consider CH3 only. CH3 is activating and it is ortho-para-directing. So this is the ortho of CH3, and this is para of CH3. This carbon is not available for the reaction because here NO2 is already bonded. So I can bind bromine to the ortho position. So here ortho position is getting one bromine. Next given SnHCl. SnHCl will convert NO2 into NH2. In the place of SnHCl, I can use FeHCl. You are knowing this concept. NaNO2HCl at temperature 0 to 5 degrees Celsius or in Kelvin 273 to 278 will convert primary aromatic amine. This is a primary aromatic amine into diazonium N2 plus and Cl minus. And if H3PO2 or ethanol type reducing agents or mild reducing agents are given, H3PO2 or ethanol like mild reducing agents are given, then this N2 plus is displaced by hydrogen. And last to your knowing, strong oxidizing agent and heating, so this CH3 will oxidize into COH. Okay. So now second last chapter, test of functional groups. In test of functional groups, one is a test of unsaturation. For test of unsaturation, we have two tests there. One is bromine water test, or we can go for Br2CCl4 test. And another is Bayer's reagent test, or named as Bayer's test. If bromine water get decolorized or Bayer's reagent cold dilute alkaline KMNO4 get decolorized, it is the test of unsaturation. Decoloration of bromine water of Br2CCl4 and decoloration of Bayer's reagent cold dilute alkaline KMNO4 is the test of unsaturation. Test of unsaturation is confirmed if both the tests are positive. This is the test of unsaturation. Next one, test for alcohols. For alcohols, we have three tests. Directly they can ask name: steric ammonium nitrate test, iodoform test, and Lucas test. Okay, in case of iodoform, I said one concept to you earlier, same I am repeating again. CH3CHOH, here it is HR or pH, and CH3C double bond O, here it is HR or pH. If these two conditions are given, and you are giving I2 in the presence of base, or they can write NaOI also, then CH3 attached to CHOH or CH3 attached to CO. This part is coming out as CHI3, which is giving yellow precipitate, and remaining part means this thing, or here this part will come out as carboxylate. Means another compound what I'll get here is HRPH, C double bond O minus, Na is taken, so Na plus. This is what iodoform test. This is what iodoform test. Who is giving iodoform test? All compounds which are having CH3CHOH group or CH3CO group. Other side is HR or pH. HR or pH. CH3 attached to CHOH or CH3 attached to CO. In the presence of I2NH is coming out as CHI3, which is giving yellow precipitate, and other part will come out as carboxylic acid. Here I want to say one more concept. If this thing is given to you, RC double bond O, for example, I can take here CH3 C double bond O NH2. If this is given and they are giving Br2 NaOH, Br2 NaOH or NaO we are hitting. In this case, don't go for iodoform. Here I said na CH3CO other side HR or pH. CH3CO other side HR or pH. CH3CO present, but other side is not HR or pH. It is NH2 in this case. If CH3CONH2 given, then this thing will be removed. Remove this thing and attach other two. CH3NH2 I will attach. Here I will get CH3NH2. This is named as Hofmann-Bromamide degradation. Why I am writing this thing here? Because sometime few of you are getting confused in this part. That's why I'm emphasizing if CH3CHOH or CH3CO given and other side is HR or pH, means hydrogen or hydrocarbon. H is hydrogen and this is hydrocarbon. H is hydrogen and this is hydrocarbon. Then only CH3 attached to CHOH or CO will come out as CHX3. If it is I2, then CHI3. Br2, then CHBr3. Cl2, then CHCl3. If this condition given, it may be some group also, not necessarily CH3. So I can generalize also by writing here some group, let's say R. Assume it is R. R, for example, here it is, okay, I will write here. Assume this thing is given, RC double bond ONH2. And now I am giving Br2 NaOH heating, or they can give NaOBr also. This R could be CH3 or any other group. In this reaction, remove this CO as Na2CO3, attach remaining RNH2, just attach. It's simple na. Remove this, go out. Attach RNH2, you will get RNH2 here. Here you will get RNH2. Here you will get RNH2. Primary amine, it is known as Hofmann-Bromamide degradation reaction. Are you understood? Pakka clear? Answer please. Is it clear to you? Is it clear to you? Understood or not? Hello. Answer please. चलो ठीक है okay, very good. Okay, so done. I was saying that for alcohol we have 3 tests. Steric ammonium nitrate test, they can directly ask name. Iodoform test, discuss in detail, and Lucas test. Lucas test, they can simply ask the reagent. Lucas reagent is concentrated HCl and anhydrous ZnCl2. Anhydrous ZnCl2. Okay or not? Reactivity order of alcohol: primary alcohol, secondary alcohol, and tertiary alcohol. So 3-degree alcohol then secondary, and secondary more than primary. So if they are reacting with the Lucas reagent, they will give alkyl halide. Reactivity of tertiary alcohol is high. So this will immediately give turbidity of the alkyl halide or alkyl chloride. Okay, or it can separate layer immediately. In case of secondary alcohol, this will take some time, like 5 to 6 minutes to separate layer or to give turbidity. In case of primary alcohol, turbidity will appear after long period of time and layer will not separate. So here possible questions are Lucas reagent, HCl, ZnCl2. If it is a primary alcohol, see you can observe it. It is given RCH2H, RCH2H, primary alcohol. Second given R2CHOH, secondary alcohol. This is given R3C, R3COH, tertiary alcohol. Primary alcohol, either no reaction or slow reaction. Secondary alcohol, reaction taking few minutes, and tertiary alcohol react immediately. Just by shaking also it can react. So primary alcohol, layer do not separate, reactivity is very less. Secondary alcohol, layer separate within 1 to 5 minutes, and tertiary alcohol, layer separate immediately. Okay, got the concept or not? This is Lucas reagent test. For phenol, directly they can ask name, ferric chloride test, or better to say neutral FeCl3 test, neutral FeCl3 test. From this part they can ask question, for the test of phenols, what we are using? First option acidic FeCl3, second option alkaline FeCl3, third option neutral FeCl3, fourth option all. What to answer? Neutral FeCl3. For the phenols, what we are using? Neutral FeCl3. Neutral FeCl3. Neutral FeCl3. Okay. In case of phenols, we have one more, phthalene dye test. So directly memorize these two names. In case of phenols, we have two tests as per our syllabus. One is neutral FeCl3, neutral ferric chloride test. Neutral ferric chloride test, and another is a phthalene dye test. Next is aldehyde and ketones. This is discussed earlier. In case of aldehyde and ketones, if you are giving 2,4-dinitrophenyl hydrazine, this H2 and this O removed as water, and I will get double bond between C and N. This compound will form, which is named as 2,4-dinitrophenyl hydrazone. It is actually colored solid, and that is why 2,4-DNP is used in the identification of aldehydes and ketones. It cannot distinguish. 2,4-DNP cannot distinguish aldehyde ketone. It is used in the identification of aldehyde and ketones, not in the distinction. Okay or not? Another is a Tollens reagent and Fehling solution. In case of Tollens reagent, reactive part is AgNH3 twice plus. They can directly ask question. In case of Tollens reagent, what is the reactive part? So answer is AgNH3 twice. AgNH3 twice plus, and this reaction is performed. in the basic medium. That's why OH minus written here. In case of Fehling solution, it is a copper 2 plus complex. Okay or not? Here also reaction performed in alkaline medium. Tollens reagent can react with the aliphatic aldehydes as well as aromatic aldehydes, both aliphatic as well as aromatic aldehydes. While Fehling solution reacts with the aliphatic aldehydes, and it is not going to react with the aromatic aldehydes. Okay or not? Tollens reagent react with the aliphatic as well as aromatic aldehydes, and Fehling solution is reacting with aliphatic aldehydes but not with the aromatic aldehydes. Okay or not? In case of Tollens reagent, this given aldehyde, will oxidize into carboxylate. Sir, why carboxylate? Arey, medium is alkaline na yaar. In case of Fehlings also, given aldehyde is getting oxidized into carboxylate. Why? Medium is alkaline. In case of Tollens, this Ag plus is reduced into the silver, which is giving silver mirror. That's why sometimes Tollens reagent test is also named as a silver mirror test. In case of phalanx solution, this is giving precipitate of CO2O. Okay, got the concept now? So this is about the test of aldehydes and ketones. Next and last topic, preparation of organic compounds. Preparation of organic compounds. Here I will tell you very simple. I will conclude everything in the reaction part only. I will conclude everything in the reaction part only. One is preparation of acetanilide. Preparation of acetanilide. Okay. Preparation of acetanilide. Okay. 1 minute. Okay. I'll use this thing. So we have this compound aniline. We have this compound aniline. Okay. Now I want to convert. What is the given name? Acetanilide means attach acid group to the aniline. So aniline is given. I will attach acid group CH3CO. CH3CO. This group is named as acid group. So this is aniline. This is aniline. And this is a CH3CO acid group attached to the aniline. So name become acetanilide. Name become acetanilide. Okay or not? Here, if I want to go for this conversion, one possibility I can take acetic anhydride in glacial acetic acid, or another condition I can take acetyl chloride in the presence of pyridine. Logic is very simple. This nitrogen will attack on this delta positive carbon and this will come out. Here this nitrogen attack on this delta positive carbon, Cl will come out. In this case, who is coming out? CH3COO minus. CH3COO minus will take H plus from here. So this part will come out as CH3COOH. In this case, this Cl minus will take H plus from here. So will come out as HCl, which is immediately neutralized by the pyridine and become pyridinium chloride. By HCl is acid and pyridine is base. So acid base reaction will happen and this will easily go in the forward direction. So what I am doing here, you can check clearly, CH3CO group is binding to the nitrogen. CH3CO group is binding to the nitrogen. So name of the compound become acetanilide. Here what is in two important questions they can ask. First of all, how to perform this reaction? So whenever performing reaction with acetic anhydride or acetyl chloride, they are highly sensitive for water. So perform this reaction in dry conditions. Everything must be dry. Everything must be dry. Okay, na? Anhydrous aniline, dry pyridine. Okay, everything must be perform reaction in dry condition. This is the one important point. And second important point, out of acetic anhydride and acetyl chloride, which one is better acetylating mixture? So answer is acetic anhydride is better than acetyl chloride. Why it is better? See, both are sensitive for water. Acid chloride is more sensitive. So its handling is very difficult. Acid anhydride and acid chloride both are sensitive for water, and acid chloride is more sensitive because chlorine is very good leaving group. It will react with water vapor easily. So its handling become difficult. So two questions are possible. One question, how to perform this reaction? Answer is in dry condition, because here reagents are acetic anhydride or acetyl chloride, both are sensitive for water. So I will take everything in dry condition, aniline pure and dry, pyridine pure and dry. Obviously they are also moisture, means in the absence of water we have to perform reaction. And second question, out of acetic anhydride and in acetic acid, glacial acetic acid and acetyl chloride in the presence of pyridine, which one is better acetylating mixture? Answer is first. Why second is not better? Because it is more sensitive for water than acetic anhydride. That's why its handling is very difficult. This is one preparation method. And second, okay, second is preparation of para-nitroacid. That also I'll discuss here only. Okay. So we got this compound. By the first reaction, NH C double bond O CH3. Here, now I want to bind. Here I want to bind NO2 group at para position. Obviously major product and ortho is going to be major. Ortho is going to be minor here, and this para product is major. Now, how we can go for these reactions? Just observe the reaction, you can answer here. What you are binding? You are binding NO2 at the para position of this group. This has lone pairs, this is ortho para directing plus M group. So I have to give nitrating mixture HNO3 plus H2SO4. HNO3 plus H2SO4. This will give us electrophile NO2 plus, which can bind at ortho or para, para major, ortho minor. What question they can ask in the practical chemistry aspect? So here they can ask one question, in what condition we have to perform reaction? So very simple thing, while adding this nitrating mixture, when you are adding at the time during the addition of nitrating mixture, maintain temperature below 10 degrees Celsius. So use ice bath here to avoid polynitration. If I am not maintaining below 10 degrees Celsius at the time of addition of nitrating mixture, then more than one NO2 group bind to the same aromatic ring. I will not get mononitro product. So two important preparation methods. Previous case, aniline to this compound acetaldehyde. Aniline to this compound acetaldehyde. How I can make acetic anhydride or acetyl chloride? Acetic anhydride in glacial acetic acid. Acetyl chloride in the presence of pyridine, dry condition. Acetic anhydride, glacial acetic acid is preferred acetylating mixture than acetyl chloride, because acetyl chloride is more sensitive for water, so its handling is difficult. And for second case, reaction to your knowing, ortho para directing group, nitrating mixture given, electrophile bind at para major, ortho minor. What question they can ask in practical aspect? If I want to perform this reaction, I have to add nitrating mixture by maintaining temperature below 10 degrees Celsius. So tell me please, if I want to go for this, what I will use? Nitrating mixture cold or hot? Obviously I will use cold, and I will add this nitrating mixture drop by drop. And as well as I will use ice bath, so temperature below 10 degrees Celsius maintain while adding the nitrating mixture, so only mononitration will happen. Okay, so this is over, you can check it. Last topic, up to the last topic we discussed preparation of organic compound also. So whatever I said, revise it properly. Today only solve all the questions what I discussed here, and then I can assure out of 15 questions of organic chemistry, 8 to 9 questions minimum. It may be more than that also, but minimum 8 to 9 questions you will get from today's discussion only. And same I can assure for the other 2 marathon classes of the chemistry, physical chemistry and inorganic chemistry. Chalo, okay, bye bye, take care, all the best. Keep chilling, keep rocking. Be calm and cool while giving your exam. Chalo. Okay. Bye bye.